Hello, everybody. Can we continue? I'm not sure if the mic is working. Can you hear me well? Yes. Okay, so I would like to do some preparation for tomorrow's run training session. So we can move now in our OAI workshop resources to the run part. So I open it on the website or in the directory where you clone that. And basically here, if you go to this run subdirectory, here you have again the README. And here you can find the tutorial, run training. So we will move a bit and we will try to do this session, which is and setup of the directory for tomorrow. Okay, so far basically we were deploying the core network, we were running the GNodeB, and we were running the OAI UE in the Docker, in the container. We were not compiling, and now we will try to take the OAI run repository. We will try to build it on our machines. So please, yeah. So first, I have a question. Who was able to clone the OpenAirInterface 5G repository to the laptop? Because our GitLab server, there was some maintenance, so so maybe for some of you it was interrupted. So we just need to make sure that everyone has it cloned on your machines. So I would like to ask you to try it once more, because I think it should be available. It should be back, the GitLab server. But I'm not 100% sure. Yes. So please go to your home directory and try to clone the repository to your home directory. Okay, I will assist. If somewhere is not working, please raise your hands and I will try to help. So I will show you what to do. So first we will go to our home directory by running the CD and enter. So we are now in the home directory, and then we will copy this command. We will use the git clone again. I'm sorry, this laptop has a German keyboard and I'm searching for the buttons. Stefan, could you please help me?
Sure.
I don't know how to insert the command.
Sure.
So. Can I remove it? Or no? Do you have some built there?
I cloned it today.
Okay.
So maybe you can clone it again.
Yeah.
But it's from today, so I cloned it just in the morning.
So basically here it displays the command which you have to run. We already have this this directory on this machine, so basically I'm not able to rewrite it. So is it okay for you, or is it working for everyone? It's very slow, the download. Okay. So I saw that many of you already have the repository clone, so we can continue with the installation. So before we start with the installation, I have here one command which we will run because we have one bug reported with the ASN1 installation. I will just write it into the command line. So the command is vm.mmap_rnd_bits equal to 28. So this command, can you see it on the? I will try to increase the font size. So can you see it now? This command. Oh, sorry, we have to write also one more. Sudo sysctl and then set these parameters. Stefan? Is Stefan here? I'm using his laptop, so I will need his password. So the command, we can try. So here is the command to run before we start with the compilation of the OpenAirInterface. And we will just wait for Stefan to give me the password. Okay, thank you, Stefan. Okay, so we can continue now. So please go to the OpenAirInterface 5G/CMake targets. So you can copy this command. So cd OpenAirInterface/CMake targets. The next step is to check out to the big26. Okay, and we can continue now. So by default, if you are cloning the OpenAirInterface repository, then you clone the develop branch, which is the latest branch with the latest development merged. But now we would like to use the branch tagged last week. So here you can see the name of the branch is 2024.w26. So please do git checkout 2024.w26. And the next command which we will need is to install the dependencies which we will need later for a build of the Gnode B and the UE executables. And for that, we can use this build OAI with Ninja and with -I option. So once we run this build, you should start some progress of installation of all the necessary dependencies. It might take some time. So were you successful with installation of the dependencies? Is it working for you? So the next step is the compilation of the Gnode B and of the UI with for the simulation. So we will use the next command, which is in the tutorial. And basically what you can see in this command, we are again using the build OAI. Here we are selecting the -- Gnode B option, which enables the build of the 5G Gnode B. Then the next option is NRUE, which enables the build of the OAI 5G UE. And here you can see that we are specifying this W, which is used for the RF SIM. For example, if you would like to build with support for the radio for USRP, so with UHD support, we would have to select here the -W USRP option. And C here is in order to clean up a previous build. We are now building it freshly, so we don't need it, but okay, now it will take some time again to build that. So if you have any problem, I can check with you. So I would like to verify with you now if you were able to build it successfully, or did you notice some issues with the compilation? If yes, please let me know, and if not, we will start the poster session soon. So thank you everyone for attention. I hope you were able to build it for today, and tomorrow we will continue with the run training session, and we will take a closer look at the run part at the OpenAirInterface 5G repository. And now I think we can move to the poster session. Thank you very much.
Good morning, everyone. We are starting the second day of the training. So let's welcome OAI again. And
Does this work?
oh, sorry.
Yes. Okay. I will stop. Okay, hello and welcome everybody to the second day of the hands-on. It's a pleasure to see you all back today. Yes, so what do we do today? So yesterday it was mostly core network. There was a little bit of run for running it from images, and then we did some ping. So what we will do today is to get a little bit more into the details of the run. So already yesterday you started to build it yourself, and today we will use that to well, also first of all run the same thing. So just that you hopefully get a little bit more acquainted with the whole thing. Then also maybe do some traffic. And then in the run, there are multiple possible avenues that we can see. So actually in the hands-on material that we have here from yesterday, and let me open that for the moment, you see there's a table of contents. And basically for the hands-on, there are multiple things. There is, well, injecting traffic. I think yesterday we didn't do this, so we, I think, should and could do that. What will also be very useful is to actually look in the configuration file and to see what we can configure in the run, because there are actually many things. And with that said, by the way, also I think for the core network, we didn't really go into the configuration file. So if there is interest, and maybe also after lunch, we should go back to the core network and also look at the configuration file and to that. So, but what I wanted to say then for the core network, there are multiple possible avenues. The first would be to look at the so-called scope. So let me just briefly show you. This is basically, where is it? Here. I don't know, where do we have, shouldn't we have here an image? You don't see an image right now, okay, but basically the scopes are like visualization tools that will show the different channels. Yes, actually that's true. Didn't we log out here? Come on. Well, I can continue. So basically, they're these scopes. They are like visualization tools where you can see the channel, like IQ constellation and so on. Why doesn't this work? And then we can look into deploying with some splits. So in particular with the F1 and the E1 split. And finally, we could run with multiple UEs as well. So I think that may be interesting for many people. And yes, and then there's channel modeling, and there are various different things that we could look at. So I will start now with a general overview and just explain a couple of things for the run repository. So basically you can lean back and enjoy a little bit while I explain this. And well, anyway, the slides will be in white. So even though this might not work now, the actual slides, they will be visible. And then afterwards, if you could indicate what would be your interest, whether you want to more look into channel models, or if you want to run with multiple UEs, or if you're more interested into some splits, then we could maybe arrange so that we do what is most interesting for you. So with that said, well, I don't know, I will try later to log in out. Let's start with the run training and with some well, introductory slides just to get us started. So so what do we cover? I already said basically everything. In the beginning, I will explain a little bit the code repository structure because it's pretty much non-standard. Then I will maybe also just start and point out some things for like the deployment of the run using, well, from source, and in particular also to generate some traffic and so on. So then you can remember what you did yesterday, and then afterwards you do that. And then, as I said, there are these different possibilities that we can do. The one thing, if you're interested to have these slides or to have a look at these slides, basically you have here the RAN training, basically what you cloned yesterday, and in the beginning there are some instructions on how to generate these slides. Okay, so basically the slides that I will show now, they are basically generated from the RAN hands-on material. So as written down here. So a couple of words about the hardware requirements. So I guess you already well understood and have mostly a laptop that allows you to do these things, but I would just like to say why we actually insist on no VM and so on. So the first thing is, if you use a VM, then you basically simulate an entire operating system, which costs a lot of resources and makes everything slow. In theory, this works for the run, but there are a couple of complications. So the first thing is that OAI requires AVX2. So this is an instruction set extension from processors in order to process multiple data at the same time. And basically this is used inside OAI to speed up the whole processing, okay? And OAI has kind of a hard dependency on that. So the first complication with the VM is that you actually need to enable the AVX2 inside. Otherwise it will, in all likelihood, not run. So that makes it complicated. The second thing, it will be slow. And the third thing is, given that it is slow, it might not work if you, for example, later want to use a USRP or something like that. So that's basically the reason why we strongly recommend to not use a VM. So, and then for the operating systems, I mean, also you all use Ubuntu 22, I think, or at least mostly. So other operating systems or the Linuxes work. So in particular, if you have something like Red Hat or a Fedora or something like this, then it works. Actually, this laptop is Fedora laptop, so this typically works, but it's easier for us if everybody uses Ubuntu because then it's a bit more familiar. So there might be other Linux that you can also use in theory, but in practice, we don't really support it well. Something like Arch, because basically there's no support in this build OAI script, which I will explain in one moment. So, and then Mac OS and so on, they don't really work. I think you can emulate things, but what I've seen so far, this doesn't really work. And if you actually use Windows, you can use the so-called Windows subsystem for Linux. So that's something that you can install, that you download from Microsoft, and then basically you run the Linux inside. And I have seen people who already used this and the previous training make it work, but I'm not sure how exactly and so on. So that's complicated. But with that said, if somebody is interested to try that on their Windows machine to run this, in theory, that's possible. In practice, you will likely succeed. I would then also be interested if you can like feedback the steps and so on. But in particular for the training, that's not really suitable because this kind of distracts from the overall goal. Okay. But if somebody is interested in that and Linux, Windows, and just to fiddle a little bit, that might be a thing that you can try. Yes. So software prerequisites. I mean, we installed yesterday basically everything and took some time on that. If you didn't do this compilation and the installation of the dependencies, you still have some time. Maybe do this in parallel so that later we can continue really with the run. I think I didn't forget anything. So table of contents is inside the present and inside the hands-on material. So I don't show this again, and I go over this. So also here now, if you have questions, we will go over the repository. I will just explain a couple of theoretical things. And if you have questions, beginner or advanced, or if you already saw OAI and there's just like some questions that you always wanted to know, then please don't hesitate to ask and also interrupt me, okay? So that's what we basically did yesterday, but just to point it out once more, we clone here the repository, the run at the Eurocom GitLab, where all the code is, where you have all the documentation in principle, except for the training material and so on. We basically write here to check out a specific tag or a specific version. This is basically, if you just clone it, the most recent thing, what you will have automatically, so it's not really necessary, but in the future, if you, for example, want to replicate and want to see whether it still works, the best thing would be to do this here. So because then you get basically the version that we tested everything. So then there's this build OAI script. I will explain a little bit more in a moment. Then this capital I means that you want to install dependencies. You also see further down that for compilation, you need to, I mean here, like a flag to compile the genome B, the UE. This CMO is for this RF simulator, which we already discussed yesterday. The C is for cleaning. The one thing that I was asked yesterday, Ninja, do I actually have this? I have this one. This Ninja basically means that you want to build with another tool, and this basically just makes it a bit faster. If you leave it out, it's no problem. You will just lose time. So yes, and also I was asked yesterday already if somebody wants to use a USRP, so one of these radios that I have also over there. Then you would basically each time give here a W USRP in both command lines. So basically there's some additional dependencies that you have to install, and then also for the compilation, there's a little bit of extra thing that we compile. Are there questions here already? No. Okay. So, well, just a couple of words. Okay, we already said it 12,000 times. This is a repository. There is these things called branches. Yes. No, if you compile like this, then basically you can do what we yesterday also did with the container images. So, I mean, basically, if you just, the basic thing is the following. If you have, for example, just an Ubuntu 22, you install this on your laptop, then you maybe install Git, you clone the repository and run the first command here, this Ninja and capital I, which will install all the dependencies. Then you do the second one, it will compile everything, and then you're good to go, and then it should work. And that's basically also something that the CI tests, and this is all you need. And then for the USRP, you would need to install additional software. We just don't do it here because in particular in the first step, it might take long. Yeah. By the way, I was also, I mean, yesterday there were some people who told me that they are interested into testing USRP. So I have one, as you have seen yesterday. If you want to test, we can test with that also later. So the run repository is there. the one thing that I want to say for these branches, so in Git there are these branches, which is basically independent, is like lineages of history. So the main branch where everything happens is called develop for historical reasons. There's also one thing that is known as master, which typically has some older stable version, but I recommend everybody to use develop because that's what everybody tests and which should have all the features. So unless you have a really specific reason to go back and to some specific version that was tested, I personally recommend develop. Then what we do is actually we do an integration, so the people, the developers, they make some work and then they put this like on the GitLab platform. There's some code review and some testing, and then we merge each week multiple things together, and then we tag it with here this version, so year 2024, and then week 26, which basically corresponds to last week or early this week. Okay, so in each week we tag this, so this is how you also see the what is the versions and so on. And in particular, you can also, for example, go back to week 24 or week 20 if and your version has a problem. So that's why I recommend actually to stay on something more recent and not go back to master. Because, for example, the latest release is from February 2024, so this is soon half a year ago. And, yeah. So for contribution, so I mean, we already said this on the first day, I believe, briefly at least. So and everybody can contribute. There's a license. You need to sign this contributor license agreement. And then if you, for example, developed, or you don't even need to really develop a feature. I mean, one thing that people often forget is that also small bug fixes or like correcting some typos in some documentation. Also, all of these things are welcome contributions. But you always need to then assign or sign this contributor license agreement. And there are actually also two versions, one for like an organization and one for individuals. So if, for example, CSIR would sign this, then everybody can just contribute. And okay, now the stopped, I believe, but then I will continue like this. And then there's all some kind of peer review. So if it's something simple,
Robert?
also Robert, yes. Hello?
Hi, I was wondering whether you plan to show a little bit more on the contributor license process.
Which process? I can open this and
if you show, I mean, if you can show how this is, you know, on our website, and maybe walk through the different, different projects, right? So if you are contributing to the RAN and some other components, then it's one license, otherwise it's the other license, just to show people how, which one they need to sign, give a bit more clarity on that.
Okay, I will do it. The only problem is that for some reason it doesn't load. So I will come back to this later then.
Okay,
but yes.
Yeah, later maybe, yeah.
Okay,
Thanks.
so then I said contributions go to peer review. So basically this just means you put this on the platform, somebody looks at it. There's also some testing. So obviously if you do some documentation changes, it's not that relevant. And yes, so there's these contribution policies document. Okay, I will try to get the internet working. I don't know what's the problem here. Oh no, here it loads slowly but steadily. Okay, I will come back to that later. So I hope this didn't make more confusion than clarity. Basically, you need to assign one thing if you want to contribute, and then you create a branch and so on. So if somebody wants to contribute and really doesn't know, then I can also just send me an email, and then I will walk you through the different steps. And yes. Now, talking about the repository. So before I go through this, maybe just for some orientation, I will do this like manually here. Let me increase the font size. Does this work? Something like this. That's not the thing. Good. I hope you can see this. So yesterday you all cloned the repository, okay? I would like to now get it a little bit more concrete and practical. So, I mean, you all cloned this repository, and what you then see inside is a bunch of files. And I don't want to like go into too many details, but I think there are a couple of things that are useful to know, okay? So you clone this, and if you just look inside, then you see these different files that you have inside. And maybe some things are obvious. So for example, under radio, you probably have all the radios. So basically the code for USRP and other things and so on, but many things are maybe not that clear. Typically what you have in a project is probably some form of like a source folder or written SRC where you have everything. In OAI, that's not like this at all. Basically, the main things are in OpenAir 1, 2, and 3, which is more or less well, layer 1, so physical layer 2 here mostly, and then in layer 3 there are a couple of things which are in particular of the GNB communicating with the core and so on. Everything that, well, first of all in documentation you have, on doc you have the documentation, so this is where you then, if you go inside, you have, for example, also the README, which is the starting point. It is here for all the documentation in OAI, so that's very useful and definitely merits to be looked at. Yes, and then what else? In particular, in CMake targets, there is this build OAI script which allows you to build. Yes. So I invite you to open that and have a look. So just going through it once more, OpenAir is the different things for layer 1 in particular, since everything is 4G and 5G together in one repository. There is code for LTE and also for NR. So LTE is 4G, NR is 5G. Then you have layer 2. So you have the different layer 2 sub-layers, so MAC, RLC, and so on. Again, both for LTE and also in NR. You also have the code for the various splits that I already mentioned, so F1 and E1 and so on. We saw this before. In OpenAir 3, you have, well, for layer 3, and then you have multiple directories that are actually for handling images. So maybe we can come back later if there's some interest, if you want to build your own images. So basically, this would be in Docker. I think the other thing is not that relevant at the moment. I already said doc is documentation. Then in radio, there is the radios, and under, well, the one thing that is also relatively important under CIA script, there's everything that is related to continuous integration and testing, but in particular, there are also many of the actually tested configuration files. So under CI scripts, that's the one thing that you also should absolutely know. If we go into CI scripts and then conf files, there. Many configuration files for either the eNodeB or the gNodeB, and also a little bit on UE. And these are the configuration files that are actually tested in the CI, so those should absolutely work. There's a folder untested with things that are not tested. You can just ignore that. So in theory, we could also make a deep dive, but maybe it would go too deep at the moment. So we can maybe discuss later if there are some people who have specific questions. I mean, there are some things, for example, where the PDSCH is modulated and so on. So basically the PDSCH is the downlink data channel in the physical simulator to send dedicated data for one user somewhere, I mean, over the interface. There are some questions, for example, that typically pop up, such as where is the scheduler and where is the code for RC, where are some simulators, where's the E2 agent. For the moment, yeah, we can come back to this later. Now, yes, so I already mentioned build OAI. Build OAI is in this CMake targets folder. You have used this later. So we go here, CMake targets under the root, and there we have this build OAI script, and this is basically the this one single script that you need in order to build everything. And if you pass the option H, like help, then you will see many things that are necessary. So already explained here is C, like clean. The one thing that you need in the beginning is this capital I for installing dependencies. There is then for the gNodeB, this is, well, for running or compiling the GNB. The same exists also for LTE, but I guess for the moment it's not that relevant. There's also the UE, and then there are a bunch of other things. For example, there are also physical simulators if you want to test or develop something for LDPC testing. I was asked this yet later. So there are some things here for these physical simulators. So then you give this capital P in order to simulate individual channels for LDPC and so on. What is relevant? There are some things for building in general, but I think it's not too important. Let me see whether there's something. Yes, there is this build lib. That's maybe important. We will also need this later potentially for the scope. So basically you have this -- build lib, and then you build a dedicated library on top. So for example, NRScope or NRQT scope, we will see this later. And yeah, there's this Ninja script. That's what you should always use. There are some things for like sanitizers. Well, that's pretty much for developers, but if you want to debug your code and so on, those can be very handy. So then also another thing that I would like to point out without going too much into detail. So this build OAI script is basically only a wrapper for triggering other programs. So I found this in the beginning a bit confusing. It is there for historical reasons, but basically for those who know a little bit about software development, I guess you know CMake. So basically all what build OAI does is just calling CMake and then either Ninja or Make afterwards. And that is relatively important because if you just run build OAI and you compile everything, then you have probably seen it takes a couple of minutes, and you don't, when you make a modification, you don't want to necessarily want to wait for that. So basically you need to go into a specific directory, which is typically that one here. So in the CMake targets, then run build and build, which is also there for historical reason that it's like that deep down. And but basically, if you then want to build specific things, for example, you change something in the UE, then you could just type Ninja NR UE soft modem and will only compile what is relevant there. So, and let me just show this for a moment. So this is also something that you could try that. I believe we in here compiled before. So for example, just go, we were here in the root. So where we have OpenAir 1, 2, 3 and so on. And then you would go into CMake targets, run build and build. If you look inside here, you have many different programs that have been generated. So for example, you have seen now already the NRSoft modem, which is basically the GNB. And if you just want to recompile this, then it would be enough to type here NRSoft modem. So, and since there's nothing to compile, so that is, in my opinion, I mean, maybe in the beginning it looks a little bit stupid that I point this out, but if not, you would wait every time these 5 minutes, and I really want to avoid this, and I wish somebody in the beginning would have told me, but there was no training when I started with OAI. So now let me actually first of all see and go one step back for the license. Okay, so the website is super slow here, but maybe we still see a little bit for the license. Yes, so as we have seen in the beginning, OAI comes with various parts. So OAI is kind of an umbrella project for various things such as RAN and core network, then also in 4G and 5G. There is this Flex recontroller, which we will see a little bit this afternoon. And regarding the license, so almost all of them have this OAI public license, so which I also explained on the first day in the workshop, which is basically OAI's own license, which is this modified Apache version 2.0 library, license, and for which you need to sign the contributor license agreement, and basically everything such as OAI 5G core and 5G RAN, and so it's under this license if you use the 5G stuff. You need to sign the license. If you only want to use the 4G core of UE, then there is a separate license, a BSD license, and I believe then you also don't have to sign a contributor license agreement. So the contributor license agreement, as I said before, there are basically two different versions. The first one, and now let's see if the PDF would load, is this individual one. There's also a corporate one for entire companies. For example, sometimes companies, they have their developers. Then let's say, for example, was already mentioned a couple of times, NVIDIA, they want to work with OAI, and then they just do this corporate thing, and then all of their developers, they can work under that. If there's some individual, like some independent person, they sign this individual contributor license agreement. So this doesn't load. If you have a look, go to the website, OpenAirInterface, then on the top you see a menu, and then at the end you have community and, no, sorry, legal, and inside there you will find this. So that's the first thing. And the second thing that I want to point out, okay, internet is slow here, probably because I share the thing. There is something, some documentation also about contributing code for OAIs for a long time in the RAN. It didn't really exist. If you go into this README folder and you open that, then there is some contribution guidelines, style guide and all that. If you want to contribute. Other questions? No. If not, I will briefly point out what we will do next. What time is it? It's shortly before 10. So what I would suggest is I walk you briefly through this, what you will see and what you should pay attention to, and then Jaroslava will do the training here and show this for everybody. So what we have seen yesterday, the basic end-to-end setup. Basically, we will reproduce once more what we did yesterday for getting this into your hands so that you're able to do this. The first thing that you always have to do, obviously, is to start the core network. So this is basically done in two steps. First, you go into this OAI workshops NCN, and then you do this Docker compose, and then you say up. You wait a little bit until everything is healthy, which you see with this Docker PS. And then it's good. And then there is the second thing. So let's assume now for the moment you compiled everything. Then you go into OpenAirInterface 5G and then CMake targets run build. And then you can run the GNB like this with a configuration file that is under OAI workshops. So basically you go into OpenAirInterface, you run the NOSoft modem, but you use the configuration file from the workshops because there it's tested with the core network, should all work. So basically, if you just run this is the equivalent of running the GNB in the container yesterday. So basically, this is the equivalent to the Docker compose up and then OAI GNB. If you then already opened Wireshark, you will see the NGAP setup request and response. So, and then the GNB will have this periodical output with this frame number, and basically you can see that it's ready. And afterwards you open in a second terminal this OpenAirInterface CMake targets run build, and you run now the NR-UE soft modem, which is for the 5G UE, with a couple of parameters. So basically what you have here, I didn't explain before, but I'll come back to this in a moment. Also with a configuration file that is in the RAN workshop, and then it should just connect. And in Wireshark, you should, for example, see this NGAP setup. No, basically you should see in Wireshark this whole setup of the connection. So what we have seen, most have seen this with this identity request, response, authentication, and then PDU session. In the GNB at the end, you should see this NGAP PDU session setup response. In the UE, you typically also see that there is an IP address. The problem that I have seen in the recent tag is that there are some additional logs, so we might not necessarily see this, but basically if you see this PDU session setup response and sending the message, then it means that the PDU session is up. So basically the GNB obviously knows if the UE is ready to receive data or not. And yes, then we see, for example, this interface. Yesterday I also had a question about random access. So maybe Jaroslava can walk us through that. And then afterwards we can inject the traffic and do this in a moment. But yes. So first of all, are there questions here? Is it clear what we will do? I hope so. Maybe just a couple of things. Also, you see here this RFSIM option for the GNOD B. So if you run the GNOD B, you have RFSIM. That's very important. This basically activates the RF simulator. SA means that you want to run it in SA mode. That's ultra important. If you don't do this, then in all likelihood, nothing will work because already the GNOD B will not actually connect to the 5G core. And then just with this capital O, you give an option which we have given to you. So this is for the GNOD B, and that's it. For the UE, there are a couple of more options. Basically, also, first of all, you see RFSIM and SA and the configuration file. So this remains the same. This, again, just tells that we want to run in RF simulator mode with standalone. So basically, this means the real 5G mode that we want. And then there are a couple of other options. C is the carrier frequency. So if you, for example, modify this number, which you can try, then it won't synchronize because you basically won't find the cell. This band 78 tells it in which band it is, which is kind of implicitly also given through the frequency, but you need to point out because sometimes there's some overlap. The numerology tells about this 5G numerology and subcarrier spacing. So maybe you have heard about this, that there are these different subcarrier spacing and so on. I think the default is 1, but just keep it in there. And this R106 actually tells the UE what is the bandwidth. The bandwidth is here given in PRBs, so physical resource blocks, which is basically a unit in the frequency spectrum, and which also depends on the numerology and so on. And if you have 106, then you're on 40 megahertz. So just that you have heard that. And yes. Questions now? No. Yes.
I just want to know, yesterday we ran the
Mm-hmm.
so now it seems like we're running.
Yes.
So should we stop the container that's running?
Yes, if you have still the GNOD B and UE container running, then it is better to stop them. Not because, I mean, probably it will actually work in parallel, but I mean, this will be more load. So basically, I would suggest you stop everything, then you just start the core network, then you run it from source, and then it will connect. And then afterwards, what you could try, for example, is just go into this XDN container, as Stefan explained yesterday, and you could, for example, ping the UE. So, but yes, Jaroslava, can you please walk us through? So what I would suggest is Jaroslava maybe makes this walk through. So also here, maybe lean back, just have a look so that you get one more thing. And then I would suggest we all try this and just make sure that everybody is able to run this and maybe ping and see what happens. And then afterwards, we maybe clarify some things such as random access or other things. Yes.
Good morning, everyone. So we will now try to set up the end-to-end connection between the GNOD B and between the UE. First of all, I would like to ask you to check if something is running in your Docker, because I am not super sure if we switched that off yesterday, if we undeployed everything after the core network session. So you can go to the terminal. I will show you which command to use. It's the docker space ps. I'm sorry, I'm currently starting the Docker on this machine, but if you run the docker space ps, you should see the running services on your machine. And currently you should see something like this, so no services running, because as a first step, we will deploy the core network the same way it was done yesterday. So is it okay for everyone, or do you have something in the Docker running? Okay, so the first command which we will use, we have to go to the core network directory of the OAI workshops. So we can just basically copy these commands from the run tutorial. And here we will deploy the core network like it was done yesterday. So we will use the Docker Compose app-d. If you run following command, then you can see what's the status of the core network containers, and basically we are waiting for them all to be healthy and deployed. As you can see here, I have all these containers healthy, so we can now open the Wireshark. Just to explain a bit about this command, so with this -i option, here we specify any, which means that basically we are capturing the packets over the all interfaces, and this K option basically starts the capture. So if we will run it from the terminal, then it should open the Wireshark, and here we can see the capture of the packets on all the interfaces. So already now here in the top line we can set the filter to NGAP, because we would like to check later the connection of the GNodeB to the core network. So we will see the setup and the response messages here. So do you have all the core network running? Can we now start the GNodeB? Okay, okay, I can wait. Okay, perfect. Can we continue? So do you have all the core network deployed? Oh, okay, perfect. So I will open the tutorial again. Just one more correction for this command for Wireshark. Please close the Wiresharks, and we will add one more filter to the command. Not to capture everything, but just the filtered traffic. So basically here you will use Wireshark-I, then NE-K, and here you will use -F and SCTP. So we will capture just the SCTP traffic. Is that correct, Stefan?
Yeah, I mean, you want something deployed, but it's
Yes. So we can now start the GNodeB. So please switch to the OpenAirInterface build directory. So we will use this command cd and the path to the directory. Once we are here, you can again copy this command for running the NR soft modem. And what you should see is the GNodeB starting. So at this point, you should see in the bar chart the NG setup request and the NG setup response messages, because we started the G-Node B and it interconnected with the core network. So now please, okay. So now we can start the UE. So please open another terminal. And this terminal, we have to go again to the build directory of the OpenAirInterface. And in this directory, we will run the UEsoft modem. So you can again copy this command for running the NR UEsoft modem. So what you can see here on okay. So we have now the G-Node B and the UE running. What I wanted to show you a bit is are the logs of the UE and the G-Node B. So if we scroll up, so on this side you can see the UE log, and on this side you can see the G-Node B log. So here here we started to group basically, and what we can see, you can see the initial synchronization of the UE with the G-Node B. Can you still read it? And basically here you can see also the initialization of the random access procedure. So here we should be able to see the 4-step random access contention-based procedure. If you take a closer look into the logs of the UE and G-Node B, then you can see also the information about the 4 random access messages. And basically here at this point, you can see on the UE side and also on the G-Node B side confirmation about the contention-based random access procedure succeeded. If I scroll down a bit, then you can see the registration procedure of the UE to the core network. And basically the setup of the PDU session. Yes? Okay, so we can maybe wait a bit at this point.
You started the GOP and then the UE, right? So I will do that exam.
So basically this is the status which you should have. Here you can see the G-Node B log, on the other side the UE log. And here you have the UE log attached to the network. So could we continue now? Yes. Okay, so Robert was already speaking about these logs, which we can see here. So I think we can now move forward, and we can try to inject some traffic. We can try to send some traffic between the G-Node B and the UE. So what we will need for that, you will need to you will need to go to the traffic generator, which we deployed with the core network. So you can use this command to go into the container.
Now you can see that we are inside the traffic generator container. You can, for example, display the IP address of this container, which we will need later for the traffic testing. So here you can see this IP address. Now what we can do, we can try to ping this this container, this traffic server from the UE. So I will open a new terminal. If I display the interfaces here, you can see the interface OAI _UE1, which belongs to the UE. And you can see that the UE was assigned with the following IP address. Now, if you copy the command from the tutorial, then we will try to ping from this UE interface to the traffic server, to the server which is running on the core network and which has this IP address. So you can see now in the right terminal that the traffic is working, and we are able to send traffic from the UE to the GNode, to the network, basically. Is this working for everyone? Are you able to ping between the...
Okay. So I will now maybe show in this picture what we did exactly. So,
okay, so maybe I can use it. So basically we started our core network, and then we started the GNode, which is here, and the UE, and we set up the connection between the UE and between the GNode. The next step which we did, we tried to ping from the UE via the interface. So basically the UE is connected to GNode, so we try to send a ping from the UE to the traffic generator which was deployed with the core network. It's basically this block which you can see here. So from the GNode, the traffic, the GNode receives the traffic, and from there it's going via the UPF to the traffic generator here. Is it clear for you, like what we did right now? Because we did the ping, and now we will try to do the IPERF test. So we will send the traffic with the IPERF. And again, we will use it between the UE and the destination is here in the traffic generator. Okay? So basically the next step, in order to set up this IPERF test, we will go once more to our traffic generator container, and we will start the IPERF server by running IPERF 3-S option. So now we have the IPERF server running on the traffic generator container. And the next step which we will do, we will take the other terminal where we were running the ping command, and we will set up the IPERF client. So the command looks like this. We will use the IPERF 3. Then we want to bind the IP address, and the IP address which we will use is the IP address of the UE. So here we are using the -B and the IP address of the UE. Then we want to set the destination IP address, which is the IP address of the traffic generator of the IPERF server. And the last part of this command is basically the setup of the traffic. So we want to send the UDP traffic with a requested bitrate of 50 megabits per second. And if we are using this R option, it means the reverse direction. So basically, we won't be sending traffic from the UE to the traffic generator, but in the opposite direction. Once I start the command, then you can see that the traffic is flowing from the basically in downlink direction from the G-Node B to the UE. I can maybe let it run a bit longer. By default, it's running 10 seconds, so we can set it here to 20 seconds, and you can see the traffic. So basically, can we move to the next step, or should I wait a moment?
I just want to say one thing real quick. So officially we are supposed to have a break now, so when we go around you can test and so on, but let's make a break, and if you want to have a coffee or something, maybe go and get a coffee and we continue 5 before 11, okay? But we will go around and help and assist. So I would like to continue. Yeah, well, because it's almost 11 and I would like to point out a couple of things. So maybe everybody now managed to run with Wireshark. Most people, to see Wireshark, to run with traffic, to do different kinds of things. And I just want to point out a couple of things. Maybe in order. That's the first thing. The second thing, there was no multiple question about random access and how we see that and so on. So that's what I will show in the logs next. Then also with the logs, I just want to show you a little bit the correspondence between what you see in Wireshark and what you also see in the logs, because basically in Wireshark we see some exchange. You will not see everything in the logs, but for example you see that there is the PDU session setup and so on. So I just want to point that out. This is also described actually in the training materials, you can see that. Then I want to just show you briefly how you see in the logs that there's actually traffic. So we did this IPEF and so on. And I just want to briefly show you how you see that there's actually a transmission going on. And then there was one question of Stefan beforehand last week when he tested something, and he had some question about high speed and so on. So I just want to point out a couple of things with the maximum speed. But we need to wait until this compiled, so I will explain that. So now I will start here I start the GNB as before. I start the GNB as before. Okay, so we've seen that. We also see here in Wireshark that there's the NJP set of requests, set of response. Now the next thing, we still don't have here the interface, okay? Which is logical because we didn't run the UE. Now, what we do next is we do NR UE soft model. And now it connects here, so we see that there is this exchange and it's set up. At the end, we, for example, already go a little bit ahead. We see here that there's a PDU session where the UE gets the IP address 10.002. Yes?
Niemals ist dein Screen nicht.
Last what she said, yes? Oh. Yes, well, okay. Then afterwards I will rejoin the meeting for seeing the, Now, what we see here is if I do IPA and I check the interfaces, now I have here, before I had 23 VTA, now I have an interface with number 25, which is OAI to UE, and it has the IP address. Okay, that's the first thing. We see, as I said here in the logs of the UE, that this has been, this one has been updated. And correspondingly, we also see here the complete exchange. And for example, we see that there is this PDU session with source setup request. We could also now go into the details of this message, and in theory, it should be possible to see the PDU session. I believe in practice we don't see this because, let me check where this is. Well, I mean, let's make it short. If you look through that here, you can see somewhere the IP address. And before, for somebody, I thought that it was actually encrypted. Then there is nothing to decode. If you now search here, PDU address. So here we see. We have the PDU address. So basically, this is a message sent from the core network to the GNB and then further to the UE. And inside here, we have the PDU address 10.002. So this is set up here, then you have the IP address, then you can do the traffic. Before that, one other question that I was got, so how do we now see a random access? So this is a little bit tricky because you need to search in the logs and so on, but not impossible to see. So the GNB runs in the beginning and there is no connection or nothing, okay? And then the UE comes, and of course, in the beginning, also in the real system, it doesn't know whether and where there is a GNB. So typically, what is happening first in the real system, like a phone, would actually scan the different carrier, the possible carrier frequencies, and tries to find the cell. What we did in the beginning, I set with this parameter 3 and then this 3, 6 super long number, I gave the direct frequency for the UE, so it knew already where to search, but then it actually needs to still decode the cell. So I also said, and you can try, you change this number, you just write something, you add a 0 at the end, it will then find and connect. So, but what it now needs to do still is needs to find. So you can already see in the UE logs that it runs this initial synchronization. It tries to search on this frequency that was given on the command line. And then, for example, you see here that it detected a cell. So it detected the cell because it saw that there is like some energy in the spectrum. And if you then go further, then it tries to also synchronize in the frequency. So then we see here UE is synchronized, okay? So this is before anything happened. By that point, the GNB has no clue that there is a UE. So by that point here, there's probably somewhere in between here, like this client connects is this RF simulator, because of course we know the RF simulator that there's a TCP connection, but the UE, the GNB didn't get anything yet. So and then. So the UE synchronized, it decodes the step 1, so this is the so-called system information block 1, which has some system information. So it would be possible also to print that in the code. I mean, by default we didn't print because already like this way too many logs, but in that system information block 1 it says things like, okay, this is operator X and there's some information on how it can for example, detect further information and where it needs to send the preamble. And now, still at this point, the GNB doesn't know that there is the UE. And the next thing is that the UE now tells the GNB, hey, I'm here. And this is basically what we see here. We see the initialization of the first step, contention-based random access procedure. So this is a bit like evolved, but that's really how it's called also in the standard. And basically the branch scheduler, so the part that selects where to send, it says that it will send something at frame 650 slot 19, and it then also will place a branch in a position with some information, and then it gets super complicated, okay? But basically it says at 650.19 it will send something, and when we hold on the GNB, we see that at 650.19 it detected something. So basically here, the GNB then knows basically what the UE sends. It just sends, it's called a preamble, it's a little bit of energy with a number inside, but not much more. And the GNB then sees this, and for example, here it gets this preamble, this is this magic number. It also sees it with a specific energy, and this is basically message 1. Okay. So now it continues, the GNB knows that it is there, it activates the RA process, and it generates message 2. So the message 2 now is in the downlink because the GNOB detected something. Sometimes it's also noise. So you, for example, will typically would check that the energy here is high. If it's only is like 35, it might be a misdetection and so on. So it sends message 2 and it just says, okay, here whatever you be, I detected you. And inside message 3, it also says where message 3 is to be sent later on. Okay, so we send message 2 in downlink, and it sends, okay, to whatever UE this was, you can now send further information down the line in message 3 at 616.17. If you now go back into the UE logs, we see that, we'll ignore that, and we see here that it guns this random access response, sorry, this RAR. Okay, so basically RAR is message 2. It found the RAR with the intended rapid 19, so the rapid is the random access preamble ID, which it sent initially here, so we had the 19, and in the message 2, the GNB also tells, okay, here for preamble 19, you are the one who is to send something later. And the reason here being, the UE can send this at any moment, and there might be multiple UEs that send at any moment, so they send a kind of random number to be able to distinguish them further down the line, okay? So it decodes here message 2, it knows that it needs to send message 3, so at 616.17 it sends message 3, which we had scheduled here. So, and so after message 3, there's also this thing called contention resolution, because of course there might be multiple UEs that send at the same time, but there's still a chance that they send the same preamble and so on. So this contention resolution is then in message 3 and message 4 to really clarify which of the UEs might be there to get them like separate, so that the GNB doesn't think there is only one UE, but there might be two UEs that respond to the same thing. So you see there's a lot of complicated stuff to make sure that the UE can access the cell and that it might not be multiple UEs, for which of course the probability is low, but if you imagine a real network, it might happen at any moment that it just happens that two UEs send the same number at the same time. It's just to make sure that things run smoothly in the beginning, okay? Is there a question here? That's basically random access. That's also how it happens in a real system. So that's the real deal. So when I had it yesterday, for example, the logs also here and all the stuff is exactly the same thing with a roof on. So and now then we continue. Basically, after random access is complete, sorry, yes.
That's on the random access. So how do you see like the average time?
You see here that at frame 650 and slot 19 we detected something, and we see at then later somewhere, so all this here is message 3, and we see here that it received the ACK of message 4. So you first have the message 1 that the UE sends to the GNOB, you have the message 2 from the GNOB to the UE, then you have the message 3 in uplink, so again from UE to the GNB, and then finally there's the message 4, which really does the contention resolution. And after the message 4 in downlink, the UE has to send an acknowledgement. So whenever there is something in downlink, it needs to send an acknowledgement back. So we know here that we received this ACK at a specific moment. Unfortunately, we scheduled the feedback at 617.17. So basically, at 617.17, we then received the ACK. The first thing we received at 615.19, each frame is 10 milliseconds, each slot is half a millisecond, so basically this is 2 times 10, so 20 milliseconds minus 1 millisecond. It took 19 milliseconds or something. I mean, the short answer is it's quick, on the order of milliseconds. Yes. Oh no, I need to, well, I checked it, it's possible, I just don't know now, I would need to check in the documentation how to. You can add timestamps, and then you, for example, see since starting the machine or some other reference, and then you get the timestamp, and then you would also see it in there, yes. But I mean, it's a couple of milliseconds, let's say 20 milliseconds, which is quick, so. That's the first thing, so let me just start it again. So now here the same thing happens once more. Well, overall, you also saw that the time between detecting here the the preamble and until we then later here have this PDU session setup response is super quick. I mean, let me just do it once more. If you're like looking closely, there was random access and then the connection was set up. So I don't know, 200 milliseconds, 500, quick. So the other thing that I wanted to say, now we can go into Wireshark and, for example, see here this exchange, which now is multiple times because I installed it multiple times. So, for example, also we have here this initial UE message, which I believe is sent after message 3. And we have here also the time in Wireshark, which is in seconds since the capture started. So it was at second 670, and the final PDU session is at second 670.65. So it took 350 milliseconds to set up the whole thing. I mean, there are various methods. You can see this in the log, you can see this in Wireshark, you can also see this different. So what I wanted to say is then you have here some exchange. It's just this downlink mass transport, uplink mass transport, which is a name for saying that the GNB exchanges data with the AMF, but it's more on behalf of the UE, because here in the beginning we have this RSC connection, so on a radio point of view it's fine. And the GNB doesn't really have at this moment until at least here to set up anything more, but the UE still needs to do the authentication, identity, security things. So there's just a GNB that is transferring data between the AMF and the UE. Okay. So the final thing I wanted to say, I already mentioned a couple of times of this PDU session resource setup request. This is basically, I mean, before here is this registration complete and then uplink mass transport. You see it again with the PDU session establishment request. So there the UE asks to get the PDU session, and then in the core network we'll also do a couple of things like checking whether it's the right slice and all these kind of things. Okay, so it's also super complicated actually, but basically if everything is fine, the AMF sends to the GNB this PDU session resource setup request. So basically the AMF requests the GNB to set up a PDU session, and inside it has this downlink mass transport where there is also the PDU session establishment accept. So the accept is basically the response to this PDU session establishment request from the UE, but the GNB and AMF interaction actually has here the request and the response. And before we also saw then the IP address inside, which then gets sent to the UE. So if you go back here, what we are seeing, we just go up. So we're here at the end of random access, right? And then where they say this apply cell to config is basically the radio related configuration. 1 moment. Is it really okay? Then we see that here there's this NAS downlink data indication, so it's called a little bit differently in the UE than what you see in Wireshark, but basically it's this downlink NAS data. So then here there's some key stuff. So this is for security. We send back here the security mode command. You saw this also in the logs. So the security mode command that basically the AMF sends to the UE. So we see this here, security mode command. You see this also in the logs and so on. And eventually you have here then this PDU session setup, which corresponds to this PDU session resource setup request, where the GNB then forwards the PDU session establishment accept to the UE, and you see this also further down somewhere. Here it sends the PDU session establishment request, and somewhere it gets the PDU session establishment response. Okay, this is not exactly printed here in the logs, but basically at the end there's what is called the RCE configuration, where the GNB tells the UE to set up a DOB and so on, and then we have eventually here the IP address. All of this looks very complex and complicated. So if you, I mean, the bottom line is there's this random access, there's some exchange between UE and AMF to set up security and all this stuff, and then at the end you set up the PDU session. Question? Yes?
More a comment. So from the GNB, everything is going to the AMF, but actually you want the PDU session establishment request and response, and then by the SNF.
No, we discussed before whether it's inside the container or not. So we have here actually the last time when I set it up, you got a different IP address. Okay, so then you also need to be careful. So I have 10.003, and what we can now do is, as before, this docker exec -it, we go into OAI xdn, and maybe for example just do bash, and we're inside the container. We do iperf3 as a server. We just wait, and here now we have, do I have this still in the history? Yes, we do iperf3. We bind on the UE just on the host machine onto a specific IP address which corresponds to the UE. So as I said, for me now it's standard 003. So there you also need to be careful. I know a lot of details that you need to get right and so on. We send it to the XDN. By the way, also I think Jaroslav didn't clearly state this before, so just so that you see that there's something like magic that this IP address appears. Basically, if we do this IPA inside of the XDN, we see that we have here this 192.168.70.135. So this is kind of the IP address of something in the internet to which you can send traffic. And by the way, also because we have here this bind, we could of course do the same here and use this. Let me take out that. So then iperf3, we bind to the UAP address, we send now to this XDN, we send UDP traffic, we want to send 50 megabits per second. We do reverse, so this then I believe is in downlink, so typically, or maybe uplink, is downlink uplink? Well, okay, we will see in one moment. Let's take it out and let's see what happens. So then if I stop this, we already see that something is happening, okay? It will send something. And, well, I was unsure, is it downlink or uplink? Okay, and I sent also too much data, that's not good. Let me lower this a little bit to 20 or 10 megabits. So what you saw in the GNB logs was some warning that some queue filled up and so on, basically meant too much data produced. And now we sent this 10 megabits, and I wasn't sure about the direction, and basically we see here now that these counters go up, and we see TX, RX. So basically, we send data in this logical channel ID4, which corresponds to the data rate and bearer and so on, and we see that here this RX counter goes up, so we send an uplink. If we now do the reverse, then it will be in the downlink. So then this other counter goes up, okay? So that's the first thing that I wanted to say. The other thing, this was a question from Stefan now. He at some points saw 2 gigabits. And then the question is this correct or not? The first thing that you need to keep in mind is that we operate here now with channel bandwidth of 40 megahertz, okay? And if, let's assume everything was running in real time, like in a radio system, which it currently does not, but if it was, the maximum that you can reach is something around 130 megabits. Maybe you remember, well, the first demo, this was actually 20 megahertz, and I had another demo, and then we saw 127 megabits. So this is the maximum that you can achieve in downlink, okay? In uplink, it will be a little bit smaller, and it also actually depends on the TDD configuration, and there are a lot of parameters that influence so much. So, but let's assume 130 megabits. This would be the maximum. In 40 megahertz with a single layer, if you have, for example, 2 layer, then you might double and so on. Now, the other thing that I said is RSIM does not run in real time. And what this basically means is that it's, for example, possible to stop it. So if something runs in real time, like in the radio, of course, you cannot stop the GNB and debug it, because then the UE loses synchronization and the connection goes down. You can, on the other hand, because RSIM doesn't run in real time, because there is like this exchange with samples and so on, you can actually stop it, which is, well, many people think it's bad or not so good, because, I mean, why would you stop it? And ideally, you want to have it run at real time so that you can have 40 megahertz. But for a developer, it's actually good, because what we can, for example, do, let me show one thing. So now I stopped the UE, the GNB is still running, and I now stopped the whole UE in a debugger. So in GDB, so this is a tool for those who don't know to actually see what is happening inside the system. And also one of the reasons why in this training we show a little bit for the run how to run this actually from sources, because running in GDB in a container and so on and modifying might be a little bit of overhead. So most developers want to run from source. So coming back to I run it in the debugger, I stop it as before, I don't want to download anything, so we see the same logs as before, it connects and so on, but now we could, for example, just press Ctrl+C and the whole system stops. And you could go and check. And, for example, debug why something is wrong and so on. So it is not real time, because you can stop it, which is a good thing for developer, for debugging and so on. On the other hand, what this also means, since there's no real time and nothing drives the clock, it can either run faster or slower. So I don't know whether you observed in my system, because maybe a bit older laptop, because there is this meeting in the background, the system resources for me run slower, there are some machines over there that run super fast, it runs at least double the speed, and probably also faster than real time. So now I come back to the 2 gigabits per second. What I want to say is, so that I continue, so then we see it still runs, everything is cool and fine. And I now do TCP traffic. So in TCP, unlike UDP, it tries to maximize the throughput. So I just do this, and it will try to send as much traffic as possible. And we see that I reach something like 90 megabits per second, okay? Which is a bit less than these 130 that I sent. If you try this over there on this machine, you will get something faster than, a higher throughput than 130, maybe you reach 200, maybe 300. So now this additional throughput that you reach is basically kind of a additional speed factor, like that you run faster than real time. So, and we come now back to the 2 gigabits. If, for example, you have in theory 130, but the system runs double as fast, then you would maybe reach something like 260 megabits per second. On the other hand, if you would manage to do 2 gigabits per second, this would mean that you have a speed factor of 15 or so. So might be possible with certain machines. I guess unlikely because I assume Stefan will run it on his laptop, so I don't believe that this happens there. Then also you will see it because everything should run like 15 times as fast as real time, so then you cannot read any logs, and I guess that's not what happened. So the other thing of the question is what went wrong. I don't know what Stefan did exactly. Maybe, for example, what is possible, for example, if you don't bind on an interface, and this is something that we can try, but you directly go with the IP address like this. Yeah, so then we see. So then what this binding that I described before is actually important because it tells iPerf that it needs to go via the UE, and then it goes through this 5G tunnel between the GNB and the UE. And then because there's a lot of processing with layer 1 and so on, it's relatively slow. If on the other hand I leave that out, then well, the Linux kernel will try to find a direct route to this XDN. And it will not select the NR tunnel because it can directly reach, I mean, if I do this 192.168.70. Something is basically the Docker network, and it sees that the Docker network is there, and it will directly go there, and the 16 gigabits is basically the maximum that the Linux kernel can then exchange without going for the other one. So that's likely what happened. So, as a recap, I explained a little bit about RA, I explained about PDU, session logs, and so on. I showed a little bit more how to generate traffic and do TCP and what can go wrong and the different UEIP address. I explained a little bit about the max speed. I also explained how you see that there is traffic and so on. Also, one thing that I would, by the way, like to point out on that here, we see that these counters increase. But for example, you also see that this number here increases relatively fast. So now you see each time there are like 2,000 transmissions that are being made, basically every slot. If it's not the traffic, then there's nothing to send. So this number goes up in increments of 1, 2 or something, because in these intervals there's nothing to send. And finally, also in the beginning, I showed how to have less logs, which basically translate of making notifications and then changing some things. So The first problem, I think I didn't have my screen, which is a bit unfortunate, so then we could have put this online, so we probably have to some additional work. But anyway, I mean, it's a question by somebody. I was a bit of lot information, but I got multiple questions. I just wanted to explain or go into some details. So if you don't understood everything, because when you don't have that much information about 5G or other things, then no worries. Yes. Yes.
How do you find the IP addresses?
You just open a new terminal and you use the Linux 2 IP, and then you use the subcommand address, and then you get all the different interfaces, and I believe you can then also say that you want to see only OAI. Is this shown? Yes. And then you only see this one interface. And you could, for example, I mean, if I now stop, that's actually a good inspiration for. If I now stop, now it's in the debugger. So there was also a question: does it shut down gracefully? No, I will just kill it, and there's no graceful shutdown. So you also see here that the GNOB detected that the UI didn't respond anymore, so it just didn't react anymore, and it's still now here present, but out of sync. The UI just said bye without saying bye, actually, okay? And now coming back to the interface, at the moment, now we should not have any interface anymore. So you could just do this, and it says, okay, device OAI to UI1 does not exist because the process was killed, and then the Linux kernel just cleans up and takes off the interface that was there. So, but on the other hand, what we can also do now, for example, is connect the UI again, and then there will be two UIs, one which is out of sync, which was the old one, and one which is in sync, which is now the new one, and then we see after some time it cleans up, which is about 30 seconds. So after some time it waits a bit, the UI is out of sync, because actually there's also something which is called the re-establishment. For example, the UI might lose synchronization, but then can come back. It doesn't need to do the complete setup, but can like resume the connection in some sense. So the GNOB keeps the context for some time. In case the UI come back, then after 30 seconds it didn't come back, then it just cleans up. Yes?
One comment about this IP story, because actually I used to correct the address, but in the output of IP I had a lot of packet loss.
A lot of what?
Packet loss.
Okay.
So basically I send it unlimited.
Yes.
Then there's two lines. What the sender is sending,
okay,
and the receiver. I took the wrong value, so that's careful here. So you actually take the value which is on the receiving side.
Okay, then let's let's test this. So I mean, also by the way, one thing now, there is yet another IP address for the UI that connected with 10.004, because while I connected the UI again, the old context was still there, so there was a chance that it come back, and when the AMF doesn't reassign an IP address that is already used by another UI. And the UI here didn't say that it was the old one. In theory, you could also somehow tell the core, by the way, I'm the old UI, but since we started like afresh, this is like going to flight mode and going back, and then it resumes a new connection. And then let's test what Stefan did. So how did you send this? I mean, we can just send, okay.
Minus U, then bandwidth 10 gigabits.
So you see that in total it reaches here this 50 megabits or something, but it's sending here much more. And so okay, at some point at the end we will see here the sender and so on, and you see things is full and then queue, and also here it says warning, the SDU buffer is full, I cannot send everything, and then you get here a much higher number at the sender, but the receiver really received 50 megabits.
It was in reverse now, right?
I think so.
Yeah, it's even worse than just to update, because yeah.
Okay.
Here, you know? Yes. But that is actually not the real value, so I did a mistake and I think it's very. So
you also see now the receiver on the core network side receiving 30 megabits per second, and then it was 50, so there's asymmetry, it's not exactly symmetric because we use TDD with more downlink slots than uplink slots. And yes, here 1 gigabit. I mean, normally with testing, in particular with RFSIM, I would recommend to actually use TCP, where it just tries to do the maximum and then it goes somewhere to a specific. So an uplink for my system would be 30 megabits, which I believe is probably even more than what you would achieve in real time, right? Do you know what this thing? Well, I mean, it's something, but I think it might be faster than real time. On the other hand, if it's in downlink, then it's a bit slower. And then, of course, also how fast and slow it runs depends both on the GNB and the UE. So, for example, probably the GNB could send more, but RSIM is not in real time, so it waits for the UE, and the UE is processing a lot, and then. Are there more questions? Did I forget something? Yes?
Would you just count this? These, sorry, I know you've done it a few times, but the different meaning of the counters.
Yes. Okay, so you have the frame slot information, which basically says at which time they occurred. Okay. Then in the next line, you have this block where you would have multiple 1 per UE, that's what we saw before. In the first line, first you see this RNTI, so the radio network temporary identifier. This is basically the ID on the interface. You also have the CU ID, which is basically the identifier that the CU uses. Because also you need to imagine that once EU has multiple DUs potentially, and then there might be duplication of RNTI, so cannot use, so there's another identifier of this EU. There's this. Then in sync is whether it's in sync, and before we saw out of sync. The power headroom is the power headroom here, but it expresses how much more power the UE could send based on the current transmissions. There's some books you can read, they can explain it better. We see here because the OAI as of now doesn't send it. There's actually some integration ongoing that it will send this. DCMax is then a kind of a reference DBM value. I think it's often 21 if you check on it, or maybe even something higher. Average RSRP is the average received signal radio power, and minus 44 is very good. That would be minus 120 minus 130, and it's average over 16 megahertz. So basically that's some general information and also basically some channel quality. You might then see 2 additional lines, one for downlink MIMO and one for uplink MIMO. Since we here run in CISO, we don't see anything, but it would also be possible to run both with MIMO and uplink or downlink, and then you would see additional line with rank indicator and so on. Yes. Then we have these DSCH rounds and dual SCH rounds. So this basically pertains to the HARC information, and basically you have these 16 HARC processes where you, one HARC process is basically, the HARC means hybrid automatic repeat request, and which, as I said before, the GNB sends data to the UE, and it will send some data to get an ACK or NAC, or maybe no response, then you can conclude that it's a NAC, and basically it needs to wait for some time. So basically this automatic repeat request then means if it gets a NAC or no answer, it will resend the same information. Not exactly the same information, there's this hybrid thing, there's some things where there's some other coding and so on, but it will resend the information. So, and because you need to wait, you have multiple HARC processes, and these numbers now is actually an aggregate across all the HARC processes. So what we see basically here is we have no channel modeling. In uplink we have some transmissions which can also happen. Which can happen because of real-time issues at the UE or other things. But let's maybe for the moment focus on the downlink or channel modeling, and we see that there were at this point at least 46,983 initial transmissions across all HARC processes. Now the other zeros mean that we never did any retransmissions, but for example if there was a number that was higher than 0, then it would mean out of these 46,900 transmissions, N retransmissions across all the hard processes. So basically, it models across all these 16 hard processes. And then it goes down because actually you can also set how many retransmission you want to do, and the number of retransmission is completely under the control of the GNOB. It can never retransmit something or endlessly retransmit something to a UE. Here by default it's up to 4 transmissions, so it means 0 first retransmissions, 0 second retransmissions, 0 third retransmissions, and if it then fails, then eventually the GNOB will say, okay, well, I cannot transmit this because channel is so bad and so on, and then there yet are there retransmission protocols in RLC. So this basically is these 4 numbers and then the errors and the same in uplink. We see that for reasons, which is not directly channel modeling, probably some threading related issues, that 24,000 first initial transmission on uplink, and then 13 times we needed to make a retransmission, but then since there's a 0, it means this first retransmission was then acknowledged by the UE. Actually, that's not true, because in the uplink, the UE just sends, and then the GNOB concludes whether it received something or not, and the retransmission is done by telling the UE whether it should retransmit something that was in the hard process before. So 0 errors, then you have the DTX. The DTX means discontinuous transmission, which is a fancy word for saying nothing received. For example, we make a downlink transmission, and I said that the UE has to act or NAC, but it might be that the UE doesn't receive, for example, the transmission in the first place, then it will not send any ACK in this physical uplink control channel, UCCH, and this would increase the DTX. So DTX, as I said, no signal, maybe the GNOB tells the UE to send something, but the UE somewhere has no signal, and then it can also not respond, and then the GNOB knows, okay, there's something wrong either in the uplink is bad or the UE didn't receive this in the first place. So this is this, and then actually this goes back into the hard process, but it's extra here because it's also kind of a useful indicator whether the uplink channel is good. For example, you might also have one thing that the uplink channel is perfect, but the downlink channel is perfect, but the uplink is super bad. You have many retransmissions, but not because the downlink is bad, but you never receive a MAC. And then you would see this, that this number is super high, and then you know, okay, well, the problem is likely in the uplink channel. Then you have this blare here, which is the so-called block error rate, which is not the block error rate across all transmissions, but only actually the number of first retransmission over transmission, and is basically used by the GNOB to decide on the MCS. And the MCS is the modulation and coding scheme, which says with what modulation and so on is being sent. So also here all this information for uplink and for downlink. Additionally, in the uplink you then also have, like here, this is again QPSK, so two modulation with 2 bits. And then you have this NPRB, which means with how many PRBs we are sending, and then SNR, which is perfect in this case. 51 is very high. Probably in the system you see, I don't know, something 10, 20, 30. So, and then we have finally the number of bytes first for the MAC. So this is the entire transport block in the MAC bytes. And the reason also what I said earlier is that, for example, now we don't send any data, no items. So here these numbers, they don't go up, but we still periodically send something. So also there are some MAC transport blocks. So this number here increases, but nothing to be sent. So this for downlink, this is for uplink. And then if we do iPerf, we see this here in the LCID 4. And the LCID 1 and 2, they are for the signaling related barrels. So we print the LCID 2, but we actually don't really use it in GNOB, in the UE, but a lot of the things are under the control of the GNOB. And LCID 1 is for all the information that we haven't seen here. So everything that is in here that is to be sent to the UE goes via the signaling related barrel 1. And all the data goes via the DRB. So that was comprehensive. We have a recording. Now I can transcribe and put it in the documentation. Yeah. So, it is shortly before 12. I guess there's lunch break now. At least me, I'm hungry. I had breakfast at 7. So it was super early. And so, I mean, maybe experiment a little bit with iPerf. I mean, for example, there are some ideas where you can play, just set, we actually do this for you. As I said, we can stop the UE, then we can, for example, just put here a 0 for a different frequency, and then the UE will never appear. Then it says actually that it cannot do this, because the frequency is too high. So let me just put here a 3, for example. And now you will see that the UE cannot decode SEP1 and then it cannot really connect and these kind of things. So you can play around. You could also set the bandwidth different or so on. You can send a bit IPERF, see how the system behaves and so on. So, but with that said, if you want to test a little bit, then we are here, and otherwise I suggest you make lunch break and we meet later at 1 moment until it continues.
You have all the Docker files, you have all the scripts, you basically have everything you need to launch and start the core network. And so that is online. But what I will do now, I will switch to my local editor, but it's basically the same what I have on my machine than there, just that you know. So everything is here and you can just get all the code from here. Right. And that is basically like now the same repository in my local machine. And okay, for the overview, I will stay here because it's larger. Basically, what is important for you here, some things are not important, like charts and CI scripts, that's maybe a bit advanced. If you like, have a look there, especially in the CI scripts, we provide also many example configurations that are actually run in the CI. So that's very interesting to have a look. But just, yeah.
Could you please share your screen, please?
Ah, yeah, I am in now. Okay, great. Hello, Camille.
Hello.
Yeah, wait. Okay. So please write Robert if there is any issue because I won't see it. Great. So let's go. Yeah, basically, so if you really want to start, there is this folder which is called Docs, and I really advise you to start here. And here you have a lot of documentation, but basically there is one file called deploy home, and basically that is where you start. So it's very easy. You see how it works. You see you have a lot of different tutorials here linked. I won't go into the detail of the tutorials now, but for example, here you could learn how to launch the core network like what we did yesterday and today is also here. But then you can also launch the core network in other flavors. For example, with different implementations, different UPFs, different config, network slicing, quality of service, like all these kind of advanced use cases, you find them here in this repository. All right, so I will now switch to my local machine. Ah, yeah, no, wait. There's one other very important folder, and that is not the docs, but that is basically called Docker Compose. And in the Docker Compose, we have, surprise, Docker Compose files. So here we have many files where you can actually launch the core network in different configurations. So here we have configurations, also database. That was actually also an answer. Yeah, I have it here. So database configuration and everything you need to launch the core network. And this, yeah, you have many Docker Compose files. And I will now go through one of them with you and also show you the configuration to do that. So basically now we are on my local machine, but again in the same repository. And for example, let's say you just want, let's just start the same kind of tutorial we did the last days. And I already showed you the Docker Compose file. This is really straightforward, but what is important here is that we mount the config. The config here, and it's called conf basic NRF config, and we mount that in the container, so the container takes this specific configuration. By the way, if you have questions, just please raise your hand, right? Okay, so I will now go with you through that configuration on a very broad overview, but for example, we can answer questions such as, how can you change the log level? Because that's actually quite important. So you see here, this file is called basic NRF config, and we will open the basic NRF config. So this is a YAML file, and it's actually, it should be quite self-explanatory. And just in case it is not, we have here in docs, we have a documentation which is called configuration. So here you have all the information, how the configuration looks like, all the default values, all the values, what you can configure, is everything in there. So really, if you want to do advanced cases and you change the core network configuration, please just have a look here. It's actually quite exhaustive, this documentation. All right. So first of all, very, very easy. Our task is to change the log level. Yeah, basically here you can change the log level. For example, if you just want to have info log level, just change it here. And actually, if you are not sure what to configure here, you can go back to this file and have a look. If I find it, yeah, here, so log level. And we can see allowed values, okay, debug, info, warn, error, or off. So now we are using info, debug level, log level. Okay, that's very easy. And then, for example, I also told you about the NRF registration and discovery. Here you can turn it off or on. And basically, one thing which is important about this config file is that this is one file to rule them all. So this is one file to configure all the core network. So basically what you can do here is also, you can say, actually, I'm interested in debug log level on SMF, but actually AMF, I don't care. I just want to see errors, and all the others should be info. That is how you can configure that. So actually, that's quite nice if you have one single network functions you want to debug. Yeah, let's keep that config. It's quite nice. Yeah. So if you like, yeah, it's Albert. Very good question. So basically, if you loaded the configuration from this file, you have to restart the container. So there is no live config update via that file. For AMF and some extent also SMF, we have APIs to change the config on the fly, but we cannot change all the values. So I think unless you know like exactly how that works, it's easier to just reload, restart the core network down and up. Yeah, and it's actually loaded into the container on the start of the container. Yeah. Okay, so we will keep the NF registration on, but for example, I will choose HTTP version 1 because it's easier to see in Wireshark later if I want to show you some traces. And then we have the configuration of the network functions, basically just what is the host name, what is the port. Very straightforward. So we have many here. Now it's actually quite interesting because we got a question regarding databases. So basically the UDR is using a database in the background. And here we can configure which kind of database to use. What is the URL? What is the location and the host of the database? So the question was yesterday, if we could have MySQL server running on another machine. Let's say your machine is called MySQL server host. You just type that and it should work. And of course, your password, database name and everything, you have to configure that here. If I do that, the config won't work anymore. Yeah, and here actually you can also change the type to MongoDB. So that is basically how you configure which database to use in the background. That's actually quite nice. Of course, you need then the Docker Compose container, but we have a tutorial for that also in this repository. Okay, so now because it's already here, I will touch a bit on slicing, but like really briefly. Basically, this is the way how you can define slices in the OAI core network. So basically, what we are doing here, because we reuse these slices a lot in this file, we make YAML anchors, and YAML anchors is just a feature of YAML of the file itself, so we can reuse parts of the config. By the way, Robert, that's a good argument for YAML, that you can use anchors. It's very nice. So it's kind of variables. Yes. Yes, it's let's call it a variable. So basically, you can define a value at some point and reuse it in another point. Yeah, it's maybe. For example, here on AMF, you can see network slices are like that. Quite nice, huh? Okay, that was easy. And here we're using, yeah, and here, you know, because basically, if you configure slices, actually, I would say configuring slices is the most challenging task in the core network, because you have to configure it on AMF, you have to configure it on SMF, you have to configure it on UPF, you have to configure it in the database, so in the UDR, and if you're using NSSF, you also have to configure it there. So it's 5 different network functions where the slicing information has to match. And if it doesn't match, your user equipment, your UE won't attach. Yeah. So slicing again is a very tricky thing. Yeah. So, but just that you know how it looks like that. So for example, basically the slicing consists of two values, the SST and the SD value, and this is how you configure it. Yeah, and then we have like specific configuration, like so far the configuration was global for all the network functions, and now we have specific configurations, for example, for AMF. So we can, for example, here we can turn on or off SMF selection, or, you know, changing some timers, or actually emergency support. And that's actually very interesting, and this is something which has to work together with the RAN. So here we have to configure the MCC and the MNC, so basically the network identifiers. And if that does not work together with the RAN, if the config is wrong, you won't see this NG setup request. You will see the request, but the response will be, I cannot make this associations. Thank you. It's called NG setup failure. Yeah. So again, yeah, you have to configure the PLMN and everything, and also the slices. And we also briefly touched about Robert told like some cryptographic things in the G0B, and here on the AMF you can actually configure which encryption algorithms and integrity algorithms are supported on the AMF. One important thing, this list here, that is based on order, like the order is based on priority. So the core will always say, I prefer this one, and then this one, and then this one. And that could make some troubles with devices, because that is basically zero integrity scheme, and zero means don't protect at all. And some like commercial devices don't like that, because it's basically only a test mode. You should not use that. It's very unsecure. But for testing purposes, that's the way. Because some of our simulators, they don't support encryption. Yeah. Yes, but a hash is a comment. Yeah. So basically, yeah. So if you want to enable encryption and you want to disable encryption, that is the way to do it. So either you delete the line, obviously, or you do that. Yeah. Okay. Yeah. Just in case you want to. Yeah. I get it. Okay. So then we can configure SMF, and SMF is actually quite interesting if you're looking at also advanced scenarios, because we have two quite important flags here. And one is the use local subscription info. And that is basically SMF has this local database of users. And it's a very basic feature, and that's just something we do for our mini deployment. But actually, if you want to have the real 5G core network, and you have all the information, subscriber information getting from the database, you should use no here. Because that means SMF will fetch all the data from the database, from the UDR. The same with the PCC rules. So if you say no here, it means it will get the rules from the PCF, the policy control function. And that is actually, we have an overview of the, no, I think, yeah, no, the PCF is not in that picture, but basically the UDM and the UDR is, so that's the first flag. And the other flag is you would actually connect to PCF. So when you want to make advanced use cases, when you want to have network slicing, when you want to have policy control, when you want to have traffic steering, when you want to have quality of service, you should configure it like that, because that is like basic thing. Yeah. And then we configure some other things which are not interesting. I mean, that is maybe interesting. You can tell the UE which kind of DNS it should use. So sometimes it makes issues because we have like this IP address here for the primary, and if sometimes your UE doesn't have connection to the internet, and that basically could mean that you configure the wrong DNS. So basically the DNS is then you will get to the browser and it will say I couldn't resolve that name. Yeah, and some other config, but I won't go into detail, and that's already quite advanced. Same for UPF. That is actually also interesting, because today in the morning we have seen that the UE IP address, it was always 10.0.0 something. And this is the way you can configure that. Because basically you can say with this DNN, and the DNN is like the DNN. Hard to explain the concept of DNN. It's like this identifier that the UE is saying, to connect with this DNN. Basically, then here you say, okay, for the DNN OAI, for example, always use this IP subnet. But it could also be something very different. You could even do like that, you know. Yeah. Whatever. So that is up to the operator. So here you can play around quite a lot. Yeah. All right. So that is a quick go through the configuration. So basically we have now, here, we have now seen, for example, how we can configure the log levels and also seen a little bit how slicing works. And just to show you that that actually makes a difference. Oh, I'm still running all the stuff from the morning. Yeah, let's kill that. In this one, so OAI SYN 5G FET. And for example, just to show you that this log level worked, I will just, which one I was using? So I was using this basic NRF tutorial, and basically just to show you, for example, on SNF, I think we had debug mode, so OAI SNF. Yeah, you can see we have a lot of debug messages here. For example, if we do AMF, we can see basically it prints the config and then it doesn't print anything anymore. Because we have here in the config, log level is set to error. And that means, yeah, if we go, for example, to whatever UPF, we can see we only have info log level. So yeah, that obviously worked. Okay, so yeah, that's it. And I mean, we could also check in Wireshark because we changed the HTTP version. OAI. Yeah, so we can see now we're using HTTP 1, whereas in the morning and yesterday we were using HTTP 2. Okay, any questions so far? All right, good. They still got you? Nice. Okay, so yeah, I will just continue, and like now basically we have answered these 4 questions. I will keep network slicing for the end, so we have more time. There was also another question about how to provision, and provisioning is basically the concept of, you know, configuring the subscriber information, IMSI, keys, DNN, slicing information, and so on. And basically, I will just show you that. Because currently in OAI, we don't have a graphical user interface. We have an API to configure the UDR, but basically what most people are doing is to just use the SQL config files. It's not a config file, the SQL files, which are read into the database. So basically, if you go here and you have this file called oaidb2.sql, you will see a lot of stuff, you know, to create all the tables and everything, and you can really ignore that. But for example, and you can also ignore that. I think most important here is this one, because that is authentication subscription. And here you say, okay, this is the UE with this IMSI, you use 5G AKA, this is the key. This is actually then the key which is also supposed to be in the SIM card. So this is how you configure it. So if you buy a SIM card and you have a key in there, you have to configure it also here in the core network so that these 2 things match. Yeah, and then you have other information, but that's basically the most important here. So you should use that as a reference and then just make your own configuration. So that's the authentication part. So that's everything regarding AMF. Again, AMF like is the first in the core network doing this access and authentication and mobility management. And then we also have the session management subscription for SMF. And here we have also interesting things like, for example, again, you know, the UEID, the IMSI, and then, but here, for example, we can see that we are configuring the slicing. Here, actually, you configure the SST and the SD of this device. And if the device is requesting a slice, and this slice is not provisioned here, the PDU session establishment will fail. So that is really important. Like then you actually really have to check, because the core network is basically saying you don't have permission to do that. Yeah. Yeah, and then we have other things like PDU session type, whatever, that is not very interesting. What is interesting here is that you also can configure, yep, yes, you can have more than one slice per device. Or actually, that is a very good question. No, you cannot have more. No, it doesn't make sense to have more slices per device, right? It does. It does. Thank you, Robert. Yeah, that's it. That's the way you have to configure it. Because basically here you configure also the DNN, which is in our case default. And if you have another PDU session, you need another DNN. So basically, then you can have multiple slices. But then you would actually need to just copy this line. And for example, okay, you use now slice SST1 and whatever. Yeah. And then you're using SDNN special slice or something. That is actually a very good question. You can actually also configure multiple DNNs here. So yeah, thank you, Robert.
As long as you configure multiple DNNs, then you can afford to provide.
Yes, exactly. Yeah, and it's like you just have to have this line again and again and again. Yeah, very good point. Okay. Yeah, so basically that's the way how you can provision a device. So for example, if you have your own devices, you just have to make sure to put them into this database on the start. Just very quickly, if you do MongoDB, same story, just different syntax, but basically we have also MongoDB file, JavaScript file to do the init. So basically here you see we put the values. Yeah, it's different syntax, but in the end it's a quite similar concept. All right, so that was rather quick, like half an hour to have this very easy deep dive. So are there any specific things you would like me to go through? Otherwise, I would just make a small demo for network slicing. Yes. I mean, it really depends what kind of operation you're running, but obviously, you know, if you're an operator, or at least in that case, you're kind of an operator, you need to have all these business support systems and operating support systems around. So the BSS, OSS systems of the operators, they're huge, maybe that's overkill, but you still need something where you can configure, where people can, like, okay, if it's just for one village and maybe that's something which does not change much, so maybe you could even pre-configure it here with this file, you know. But if you want to have something dynamic, like people go to a web page, they buy a SIM card and whatever, you need to integrate that. And that is just basic software stack. And that's, you have many vendors who do that, third parties, but actually you could even do that yourself. Like if you have one good computer science student, honestly, it's not hard to do. I mean, you even could do something like my PHP admin, right? If you know that, if anybody knows that, and just put stuff directly in the database. It's not very convenient, but you could do that. That being said, we also have an API to configure the UDR more or less on the fly. So basically you can put values into the database during running. So that would be a starting point to connect, for example, to your web application or whatever to provision. That's the first thing. The second thing is that we are actually going to build that. So we in OAI, we are going to build a graphical user interface that is on our roadmap. So basically then you as a user, you can just go into that, you can start it and you can type in all this kind of information. And then basically you would be ready to go, right, for this kind of use case. All right, great. Yeah, so with the last 25 minutes, I will just go through a slicing scenario, explain you a bit the concept and how it looks like in the OAI 5GC, and maybe also show you some attached, detached thing in the slicing scenario. There is one feature where I really don't have time at the moment to show you, and that is quality of service, but we're actually about to release QoS. So in 1 or 2 months time frame, we will have a new release of the core network, and there we will actually have quality of service support. And there will also be in this docs folder, there will also be a tutorial. But just maybe if I'm already here, I don't think you can read that, but we have many different use cases. So for example, this one is for MongoDB. This one is for static UE IP, which is quite nice. So you can, for example, today we've seen like with Robert's demo, when you restart the UE, it gets another UE IP. But actually in the UDR, you can configure static IP, gets the same one all the time. But that is quite a cool use case. But then we also have advanced use cases like redirection. You can actually redirect user traffic. So you can say you go to facebook.com, but it redirects you to a competitor of Facebook. They don't have MySQL. Sorry, MySpace. Whatever. But that really works. So that we have all these scenarios and also traffic steering. So you configure it to go somewhere else. And then also, for example, we have something with an uplink classifier, and that is, if I find it, yeah, and that is quite an advanced feature of the 5GC. And I was talking to some people here already about that, so I will just show that also quickly. Basically, it looks like that, your UPF infrastructure. You have many different UPFs, and this UPF decides based on the traffic where to route traffic to. So that is an ideal edge computing use case. So all these kind of things are supported, and you can configure that. It is rather advanced to configure it, but all the files are there, and you can just start from there. Yeah. Actually, yeah, that was my master thesis. Okay. So, but I won't go through that. I will go through the slicing. Here. Yeah. Okay. So, I mean, basically, the concept of slicing is just that you have one network. Oh, wait. Is everybody familiar with network slicing? So I will just do a 1-minute intro. So basically, the concept of network slicing is that you have one 5G network which serves many different use cases. So, for example, you can't have one slice with the configuration, for example, normal subscribers, mobile broadband, just like your phone in your pockets. That's the slice. But then you have a slice for robots, and then you have a slice for the police. You have a slice for firefighters, for some aviation stuff. So there's many use cases, and that's the point, that you can have like different quality of service profiles. For example, the robot has it requires low latency. So it has like a specific, low latency profile for the quality of service. And the point of network slicing is that you can do one configuration for many devices. You could even do that per device, but that's quite complex. So that's why you have network slicing, and you can do that. And that's one thing. And that's from the use case perspective. And from the technical perspective, you basically can assign network functions to a slice. So for example, you can say, I have 10, no, let's make it like here. I have 3 SMF, 3 session management functions. And this one is responsible for this slice, this one for this slice, this one for this slice. You could even, like if you think like an operator, you could say slice 1 is served by OAI SMF, slice 2 is served by Open5GS SMF, and slice 3 is Ericsson. Why not? So that's really like the key thing about 5G is like all these dynamic approaches to configure the whole networks. And that's really, yeah. All right, so given that, basically the slice itself is just identified using these 2 basically numbers. So that's the SST and the ST. Not sure anymore what the slang stands for. Thank you. So what Robert said, service type and service differentiator. Yeah, good. Yeah, the better student than me. Anyway, so but basically within the core network, that basically means you can separate the concerns. You can say this one is for that, this one is for that, and that's exactly what we did in this tutorial. So we have 3 GNode Bs actually, and each of them has their own slice configured. So we have 1 slice per GNode B and also UE. And then actually we reuse the same AMF, we reuse the database and authentication stuff, and we have one new component which is called the network slice selection function, and this one is responsible to then kind of redirect the the information. And yeah, so basically then we have in the first slice we have our own UPF, our own SMF, our own NRF. And then in the second slice, actually they share the NRF and they have their own SMF and UPF. And then in the third slice, it's all their own. But that's quite an advanced setup, but that's basically really to show what is possible. Yeah, and that being said, all of this is online. So you can just go to Docker Compose slicing basic NRF. And that's also good because I showed you the configuration before, because the configuration for this one is a bit more complex. So yeah, so basically, again, we have MySQL, we don't care about that. We have NSSF, which is now the new component. And basically here we have two volumes we need to give it. First of all, is the slicing base config, that is the config, like the one I showed you before. But then it needs another file, and that is the slice config. I will also go through that file. Yeah. So this is the selection function. I will show you later in the trace actually what it does. It's quite simple. UDR, we don't care. UDM, we don't care. Ours, we don't care. And now it's interesting because now we have an NRF slice 1, 2. That means this NRF serves slice 1 and 2. And we have one NRF that serves slice 3. And actually, you can now see that here we are using a config called slicing slice 1 config. And here we are using a config called slicing slice 3 config. Because I showed you before that like with one config file you configure everything. It doesn't work for slicing. For slicing you really need different config files for different network functions. Because otherwise it would get way too complicated. And it's already quite advanced. AMF, we don't care, there's only one. And then we have SMF slice 1 config, SMF slice 2 config, SMF slice 3, you get it? It's like a tongue breaker. And then also the same for UPF. UPF slice 1, UPF slice 2. And that's actually quite nice here because we're using, we are using OAI UPF, like our own UPF for this scenario. But actually, we are also here in this scenario integrated a third-party UPF, the so-called VPP UPF. So here we have to configure it a bit differently. Here we have to configure it with environment variables. Yeah, but basically you can see here actually we configure the slicing information 130, 130. And if you go back to our picture, we can see that is slice 3. If you can read that. I can't make this bigger. But anyway, this is orange one is the slice 3. Yeah, and here we configure it here, but for the other network functions, our own, so to say, we configure it in the conf files. Yeah, then we have again our XDN, you know that by now. And that's it, basically, yeah. So if you look at the configuration now, just very briefly, we have this file called slicing base config, and like that looks very familiar. It's the same config, again, log level, NRF, whatever. What is new here is that we have an NSSF. So it's a config for the network slicing selection function. That is the same. That is the same. No, that's not the same because basically on AMF, we need to tell it to enable the NSSF function. So we have that here. And that's it. Because basically that's the only components which are reused by the whole core network. And then we have for each of the slice their own configuration. For example, slice 1, you can see it's only SMF and NRF and UPF. That's it. So like we split the configuration. And for example, here we just define slice 1, which is 128 and 0, like 00080, which is again, yeah, it's 128, 128, right? That's a bit tricky, by the way, right? This SD value should be a hex value. And in many places we put in a decimal value, and we have just recently fixed that. So basically the configuration I'm showing you now is already updated in the develop branch. So in the develop branch, you really have to be careful to get also the newest configuration files because we are now using an hex value for all the SD values. So there was a breaking change, just so you know. Anyway, Then we have our SMF, and SMF is the same config as before, but basically we're just saying it use slice one, use slice one. And if you go to the others, it's the same. Again, SMF, the difference is use slice two. That's it. That's the whole slicing configuration. Yeah. Okay, yeah, so that's basically the network slicing scenario. And I will stop that core network we started before. And now I will just walk you through the network slicing tutorial. So I will start the core network, and then, so if you go back to the picture, I will start all these core networks, all at the same time, all the different slices. And then I will start the first UE and G0B, the second one, and then the third one. Just so you know what is happening in the network. So basically, if you do that at home, it's very simple. You just say docker compose, basic, no, not basic. Yeah, it's called slicing basic NRF. So you see that is the whole name. And basically, like we did today and yesterday, just select that file, give it -F, select that file and say up. And now it's running. And I will do a trace. So again, yeah, starting Wireshark. Filter it for some interesting protocols. Maybe let's skip HTTP2. Yeah, better. All right. Okay. So now the core network is running. We can and should actually check if the core network is healthy with using the docker ps command. And actually, if you remember in the morning, we had like 5 or 6 components here. So now we have much more because we have more SMF slices. And now I will just, let me check. Actually, I want to start with slice 1. And we have here this slicing runcing. So basically, we have here we have now, there was a question about run simulators. So here just quickly is an example to use different run simulators. Here we are using UE runcing, which is an open source run simulator. Here we are using the OAI, like we had so far. And of course, G0B and UE. And here we have G0B sim, which is another open source run simulator. So we integrated all of these here ready to use. So you can just have a look at that. Alrighty. Yeah, so we see everything is healthy and fine. I wanted to check which one is slice 1. Actually, it's not really important in which order I do it. But just to, yeah, 128 is slice 1. Okay, so that's actually the UE run sim. And also here in the config of the UE run sim, you can see we configured the slice here. And it's like 128 and SD is 128. I don't know why we have put these. I will need to check that. But anyway, so we configured the slice now also on the UE side. And yeah, and so we can just say docker compose, slice, docker compose slicing, run sim up. How did we call it? UE run sim. Yeah, and that's it. And we should actually see, yeah, sending PDU session establishment request. Hi. Welcome to the demo effect. So we can actually see that the session establishment request was not successful. And I also know why. Basically, I am really sorry for that. That is why basically you should not use develop images, or you can use them, but you have to be careful. Yeah. So let's see. I will need to repull it. Let's see how fast it is. Basically, I was using another version of SMF where oh, that was very fast. Okay, so that's great. Okay, I am sorry for that. It should work now. Yeah, basically, I was using my own development branch for that, and it's not, the interworking doesn't work because, again, we made breaking changes. So we just have to pull now the new images, AMF and UPF. And now it should actually work. So we will restart our trace. Doesn't work, I have to restart Wireshark. Demo OAI. By the way, just in case, if you only do the core network and you're not using, I am using RFSIM. Because we are using RFSIM as well, so I need to put the capture filter like that, what I told everybody in the morning and I forgot myself. Good. So I'm just copying this capture filter here. I will put it here and we are ready to go. Yeah, great. So you see we have the stuff. Now we filter for some interesting protocols. Again, we do the same steps as before. Docker PS, we check if they are healthy. They are all healthy, and so now we can start the UE. -f, Docker slicing, runsym, up E runsym. And now let's see what's happening. Come on. Okay. Okay, that is actually quite interesting now. Okay, that is really the demo effect. Let me quickly check something. I can actually also show you why it failed, because that is maybe quite interesting. Because the way it is working now, we get from the UE, we get the PDU session establishment request at this point. It is encrypted, so we don't see it, but we know that this message actually contains the PDU session establishment request. And here we had all the authentication that already worked. Now we can check what is AMF doing. And now that's actually interesting because the AMF is with this, if you can read it, it is telling, it is sending a request to the NSSF, so to the network slicing selection function, and telling it, okay, please give me the SMF, or actually give me the NRF, give me the network functions for this slice. That's how it works. So that's why it's called selection function. And it replies with a 400 bad request. And that is the reason why the video session establishment failed. I'm not 100% sure why that is the case, but I think that's because I did something.
Sorry.
Yeah.
I think on the database part, you had shown that you had registered 2 slices. Yeah, I was just trying to figure out. Are those 2 slices the ones that you linked to the slicing configuration that we were able to set?
In this one, actually no, because that's a bit a detailed thing. Because actually in the SMF config, we're saying use local subscription info yes, and that means it takes the local subscription infos which is configured here, and here we configure the slice. But you're absolutely right. If we would say no here, we would need to configure these slices also in the database. Yeah, it's a very good question. Yeah, so Yeah, it's still running. So I'll just try one more thing, and if that doesn't work, I fear that we have to give up, because that is really the live demo effect. So what I'm doing now is quite important for you, because I have this NSSF and it's already quite old. I never updated it. So sometimes it's very good to just delete, or actually you don't have to delete them, but just to repull the newest images, because we update them all the time. And if you're using Docker Compose, it will not update the images. So just from time to time, update all the images. And I am doing that right now. And then I am hoping that it just works. And just to be safe, come on, just to be safe, I will also check out the master. Yeah, you see, sometimes it can be quite tricky. But actually, normally we always ensure, like these tutorials, they're always working because they're running in our CI. So what I'm having here, that's a local problem, because they are actually, should be correct. So I will just restart it, and we see we're now pulling the new NSSF. Yeah. Come on, okay. Okay. So we're now again, we started the core network and we're waiting again until everything is healthy. So we can actually see here it's still starting. Still. By the way, you can also use the watch command, but I'm always too lazy to do that. So yeah, we see everything is healthy, and hopefully, if we do that now, it will work. So again, we start the UE run sim, and it's not working. So actually, there is a problem. Actually, there is not time to debug that right now, but yeah. Oh no, sorry, I was wrong. It just took quite a long time. Actually, we can see now that the connection setup is successful. So we actually got the IP address 12.2.1.2. And if we have a look at that, it's again uplink transport. Yeah, here we had this message before that failed. And here we actually get AMF telling NSSF, okay, I have a request for this slice. Which kind of component should I use? And then basically, yeah, this one, and then basically here, like in the protocol itself, it tells us, okay, we should use actually this NRF, this IP address. So that is basically how we can select all the different slices. And then it's just a normal procedure, like to connect everything and have video session establishment and so on. So that's for the first one. And just to be sure that it works, we can now also start the slicing run sim, Chinook sim. No, should not forget up. So basically we're creating another one. So I will also restart the trace to see what's happening here. Yeah, but we see we got an IP address. So here we have another IP address. And actually that's also interesting now, because we have configured different slices and also different networks. So here we have the IP address 12.2.1.2, and here we have the IP address 12.1.1.2. So that's basically based on our configuration. Yeah, and I could now do the same with the Geno PSIM, but I think we've seen that it works. And now these two devices, they're in different slices. And now you can do everything else, like having different quality of service profiles and everything for the different slices. So yeah, that's it for this tutorial. I'm happy that in the end it worked. So again, if there is issues like I just had, it's always a safe bet. Delete your local images, repull them, go to your repository, check out the newest version. Maybe go also to the master branch, because this one is stable. Yeah, so if that happens, just follow these steps. It's actually cool that it happened, so I could show you how to fix it. All right, so are there any questions regarding this or anything regarding the core network? Because now we will go to the OEM part shortly. That's actually a question for Robert. Is that supported by the OAI GNOP?
Not in development. In OEM, then there is a small slicing demo in try, but I think there's no ownership. Anyway, I mean, and that's a work in progress, and at least in GNOP, it's on fully done.
But that's a good point. I think if that is done in the GNOP, we should update this tutorial to actually show that like several UEs are connected over the same GNOP, but the UEs have a different slice. Yeah. So, like if we have this one, actually have one GNOP here, different slices. Yeah, and then yeah. Okay. Anything else? Yeah, that's a very good question. That goes more to the quality of service thing. Like the slicing is the concept, but basically what you want to do with slicing is having different QS parameters. And there is the concept of priority. So basically you have different quality of service flows, they're called in 5G, and you can give them, for example, a guaranteed bitrate. So if you have, for example, like let's say your channel is 100 megabits, it can do that throughput. And if you have one guaranteed bitrate of 80, with a very high priority, and one with 60 with a low priority, what should actually happen is that the one with 80 should get everything. And then the one with the lower priority gets less. And that is, for example, how you can ensure that a very important service gets what it needs. That is like the concept in the core network, and that's also in the UPF, but actually the work to be done, like all this scheduling and actually ensuring that, is also a lot on the GNOP. So actually that would be a very interesting question, how you do that in the scheduler and everything, but maybe that's too advanced. But I would like to know that as well. Yeah, but in the core network, it's like you configure that and that's how it behaves. And like the QS is really a own topic on itself. Like there is so many QS parameters. There's so much to play around. There's also this ARP, like this allocation retention policy, basically saying if another flow comes and your resources are full, it could get rejected even. So the PDU session establishment would not work, or even kicking out other UEs. These kind of things are all possible. Right now, not in the OAI, but in the standardization. Currently not, but at least in the core network, we are working on the UPF also on the QS enforcement part. So actually the UPF would make sure that you get your bandwidth, but that's on the UPF part. And then if the GNOP doesn't play along, it's basically what you said, it's a effort. Yeah. Yeah, I think the most basic use case for quality of service is like we all have, we buy a subscription from an operator and they tell us you have 50 megabits. That is basically the killer use case, but that's kind of boring. Yes. Again, yeah, I don't quite follow.
Yes. Would it take long to try to configure an experiment where we would have two slices and you would run some traffic?
No, of course not, because it's already there. Again, the GNOP needs to support the slices. Also, you need to support of QS to actually make that experiment. But at least from the core network side, that is already there. GNOP is working on that. But you could even use that core in like a commercial GNOP, which has this support, and you make your tests. And that's not much effort. That's basically all there. Yeah. All right. So I think time-wise, we have to stop here because Robert also needs time to show his part again. So I thanks a lot for the interest. If there's any more core network questions, you can also ask me in the break. Thanks a lot. We are making, boss is saying we're making a 10 minutes break. So see you again at 14:48. So 10 to 3, please. Camille, we are making a break and I think we're also doing a laptop switch. So Robert will connect again.
Okay, guys. Hello? Can you please have your attention? So we are a little bit on the final 100 meters. Nevertheless, there are still a couple of things that we can see together. There were a couple of kind of questions from people what they wanted to see in the run. There's also the operations and management part with like this E2 and so on that I wanted to briefly show so that people can use it. So now for the last, well, 2 hours, well, one, I mean, try to hurry up. I will go rather quick. There is one part that you can do together with me, which is basically running with FlexRig, so the E2 agent and the near real-time rig, and then we see something in the accepts. Otherwise, I also have a little bit on the run. So if you want to follow the FlexRig, I mean, I guess maybe afterwards we can check individually, but otherwise I will go straight now for the end and just show it. And if you want to follow, the one thing that you have to do now, if you want to follow. So basically, if you want to do the FlexRig stuff, and I will explain this a little bit more in detail in a moment, what you have to do is you need to go to CMake targets as we did before. Hope you can see. And you need to build in a specific way. And it's relatively important to do it now because it will clone a little bit more and so on. But basically, you go to OAM, there you have everything, also the explanation of how everything works and so on. I will show some parts, but the important thing basically is to build with this build E2 switch, okay? So I will do this now so that I'm sure that I have it. I will also show you one additional thing so you know all of these options. There's this clean, there's Genome B, there's NRUE, there's Ninja. The new thing is this build E2, so we will see this in one moment. And otherwise, the one thing that I will add now that you don't have to add, you can, is this option D, which basically writes everything that has been compiled in another directory. So, and also this you find in the build OAI help or somewhere else. Have a look. Actually, I think we can probably also see this somewhere. Can we see this at the end probably? Yes, so now it goes into here. So basically before it was CMake targets, run, build, and build, and now I will have E2. You can already start to compile this only with that. It might take a little bit of time also because it needs to clone FlexRig. Do that, otherwise I will, as I said, go more or less directly, cover a little bit on the run, explain a couple of things. I don't think I have too much time on E2, and make this demo, and it's relatively straightforward. It's just a couple of additional calls plus what we already had before, so you can reuse everything that you had before, and then yes. Okay, let's just make one quick recap. So before we saw that we had to start the core network, so this we know that very often. There's here this Wireshark call that I will also update later, so that you always use this capture filter, what we have seen, so that it doesn't get too big and then fills the entire disk and everything. We were running the NRSoft modem, so the Genome B with a specific configuration, and then in Wireshark we see the NG setup request and the response. Then we also started the NRUE soft modem, which is the UE with a specific configuration. Then we saw the PDU session set up. We on the Genome B, we also saw the same on the UE here with the IP address. Then the interface and how to see that. We generated some traffic. So this is on the next page, and already get the feedback that's a little bit confusing. So I will try to afterwards clean this a little bit up. But nevertheless, we saw how to ping, we saw how to use iPerf, how to generate some traffic, how it affects the counters, and so on. So all this, I now assume that you have more or less understood what you can do and how. And I wanted to first also discuss a couple of things of the configuration file. So unfortunately, we don't have such a nice documentation like the core network, or at least not yet. So for example, or in particular, there's not a single document that summarizes it all, which is a bit of a pity. And I hope we can do this now in the second half of the year, because it's actually really useful. And there are a lot of configuration options that also seasoned users don't really know. Yes, but I want to walk through a couple of things. I go into the, I will orient a little bit on the configuration file that we just used for running the RFSIM. Let me actually go into the run, and then we had conf here, and there are multiple configuration files. So you already see there are also other configuration files for F1 and E1. After having discussed a little bit the configuration file briefly, I will just show you quickly also how to run E1 and F1 splits. But before I do this, I will just take this configuration file here. So, and there we have our configuration. So a closer look at the configuration file. The first thing that you should know, what is important, you see here in the top, you have this active gnode bees, which is a list actually. And then in here, you have this gnode B section and then a name. And these two names, they have to match, okay? That's just the one thing that I want to point out. I think actually it's not written down. Maybe we should write it down. If you have a mismatch there, then the configuration won't work. And this is for reasons of history. And well, then what are the different configuration options that we can give? Basically, in the beginning, you can also set the SA mode in the configuration file like this. This was the --SA, what we are giving before. So we are also starting to integrate more and more options into the config file, because otherwise you have so long things. Then you can give a gnode B ID and this gnode B name that I already mentioned. So that's relatively self-explanatory. Then we have here this PLMN list. So this was something that we saw in the core network before. So there we have the MCC and the MNC and the MNC length. So these three actually together are the PLMN in itself. So the MCC is the mobile country code, and then the MNC is the mobile network code. Typically, so you have for different countries the MCCs. I know that, for example, for France it's 208. I don't know what it is for South Africa. So ideally, you better do not use the South African or whatever. Ideally, you just use 00101, because this is the test element. Okay, so just have seen this. Then there's also the NSSAI list. So this was the whole discussion before with slicing and so on. So in the gnode B config, you can give these slices. So here you see SST equals 1, and there is no SD. The SD is optional, and if you have SST1, then it means enhanced mobile broadband. If you only have SST2, then it's ultra reliable, low latency, and so on. Okay, so just that you have seen that. There's also the tracking area code, which is an ID to group gnode Bs like in regions and so on. So for UE core signaling and so on. So these are the two here at the top. Then let's see what we have here. There's one thing that I want to point out. There is this minimum RxTX time. So this is the so-called minimum feedback time. Maybe you remember before I was discussing that the gnode B sends something in downlink, and the UE has to acknowledge this. And basically, there's a minimum time between when the gnode B sends something and the acknowledgement. And the important thing is that typically for all the UEs, when you use a phone or something, it's 2. The OAI UE can be set to 2, but it's a bit tight timing wise, so it's wise to set this to 5. So for example, here we were running with RFSIM, and here was actually set to 6. Okay, that's the one thing. There are a couple of other things. For example, you can enable and disable SDAP if you have heard about this. You can, for example, also activate multiple layers, or actually multiple antenna ports. I mean, there we get really into details which are a little bit complicated. But basically here, when this is both set to 1, then it means single layer. Single antenna port, which will then translate to single layer. Yes, so then if we go further down in this config, by the way, I hope you can, it's okay, right? Get a bit wider. So you have this in your thing in the workshop material. So you can also read this once more. We have here then the serving cell config common, which is actually like something that comes from the RC, but basically here this is radio configuration. You have the physical cell ID. This is an identifier that the genode B radiates. Then there is the absolute frequency SSB. So the SSB is the system synchronization block or something like that. So this is basically the frequency on which the genode B sends this SSB. Then there are also other frequency related things. For example, this point A, which you maybe have heard, which is basically the leftmost border in the frequency. So there are a lot of really low level detailed things, but basically this absolute frequency SSB and the DL absolute frequency point A, as you can see here on the left, those are the parameters that you have to set correctly if you want to put the the genode B or the cell, the radiate cell at a specific frequency. And as I also wrote here, you can try to understand this. It's also in the end not that hard, but there are calculators that do that for you. So then there are more things. You have the bandwidth parts and also the same then for uplink, and then you have various things for random access, and it's very detailed actually. You can set a lot of things, and you can in particular also break a lot of things. So if you misconfigure certain things, then it might be that the UE doesn't connect at all. Okay, so always do with a bit of care, also back up your files and so on. The one thing that you maybe want to modify, because it's also interesting, is here these parameters NR downlink slots and uplink slots and the symbols. This is basically the TDD configuration. When you, for example, typically you have a TDD configuration, the first couple of slots, they are downlink, at the end it's uplink, and then you can set more or less and modify this a little bit. So these are, if you want to modify TDD pattern, then this is the section. So then also finally, still in genode Bs, you have here the AMF IP address. So we have seen also before in the configuration from Stefan that there was where you would configure where the AMF listens or gets an IP address in the Docker network, and here you set this in the genode B configuration, you say where it is, and then also for the genode B you set actually where is the IP address where it should actually bind itself to then communicate to the AMF. So this is the genode B section. Then one of the more important section as well is MAC RLCs here. So this sets basically the configuration for everything that's MAC and RLC. I want to point out a couple of things. As you can see here, there is like this. There is this ULSCH max frame inactivity, and often configuration files set this also to 0 or 1, and you might have problems with multiple UEs. Basically, what this parameter means is after how much time the genode B will automatically schedule the UE in order to maintain synchronization. Okay, so basically every 20 frames it will schedule the UE. On the other hand, you might also use this if you want to achieve a low latency, then you can force the scheduling of the UE in the uplink periodically or even all the time, and then you get a low ping. Then there are also other things here. Maybe let's discuss first here the DL hard round max and then also DL max MCS. Basically there you can set how many hard rounds you want to do in the scheduler. You can take some influence on what is the maximum MCS. So for example, you want to make tests and limit the MCS to a specific thing, then you can set this here. And one of the important things for radio tuning, so I was also discussing here, one of the important parameters in order to make sure that, for example, you have proper uplink behavior and so on is these target SNR. And actually here it says target SNR times 10. So this is basically 15 dBs and this is 20 dBs. And sometimes you have to modify in order to adjust in a certain range with how much power the UE should send in the uplink. Okay. So, basically here is written increasing those. This can, for example, stabilize the system if you don't have that much stability. Related to that, there will also be the RX gain and so on that I will explain in a moment. But these two parameters, they are important to play with around and maybe try to understand. It basically tells, this is a parameter that tells with how much dB a UE should send an uplink, and this can make the difference of night and day. Okay, and in particular because you have to configure this manually, and well, if it's misconfigured or not properly set for your radio configuration, then you might not have proper performance. And in particular, also, as I said before, for example, you might actually have a good downlink channel. Maybe the UE can receive everything, but if then the PUCCH target SNR is wrong, then maybe in uplink nothing works, and the GNOB makes retransmissions when it doesn't need to, which can then result in low performance, like low throughput and so on. So the L1 section I will omit. The one that I think is also important is the RU section. So this is basically now really when we talk about radio unit related configuration. So the first thing is the number of antennas. So I think that's relatively easy to understand. So here in RFSIM we just had one antenna, no MIMO and so on. But then you would set this to 2, and there's some additional documentation in the main repository where you can read how you need to modify this. The other parameter related to performance, which is important, is this ATT-TX and ATT-RX. That's this. So this basically describes how much attenuation you want to apply on the TX or on the RX signal. And one of the other example is that sometimes the receiver of the UE is saturated, so the GNOB sends with a specific power, but it's actually way too strong for the setup that you have. And then you need to set this to something higher, like 6, 12, 18, in order to make sure that the receiver at the UE is not saturated and can properly receive. So typically, ideally, what you want to do is first play with that. For example, set value 6, 12, 18, find out what works good, and then try to adjust in the middle. And once you have this, then you can also play with the target SNR. So I talked to some guys here before. They have a paper, they have some nice graphs and so on, and I think the throughput, they could be better. And basically, you need to play a little bit with the gains and so on. And with that, you can actually make a lot of things. Also, the other thing, I think we can have a look at the setup that I had there and what I showed you yesterday. But the attenuation and so on is larger than 0. I think it might be 6 or 12. So that's important. So, and then there is also the max RX gain. So ATT-TX, ATT-RX is actually some parameters that are applied in the digital signal processing. Then there's also more the physical related RX gain, which is to set the maximum received gain for the USRP. So also here, there is a maximum, which I believe for USRP B200 is 114 actually here in this config file, because for RFC we wouldn't necessarily need it, but so also this might be too big, and if you reduce it, then the performance can actually be better. So reducing the various gains and so on can actually boost your performance. So, and then finally the SDR address, which you don't see here, this is a parameter inside here, with which you then can, for example, select to which USRP you talk. So, for example, you might have a server and 2 USRPs, or maybe you have a network with multiple X300 or N300 and so on. And if you want to select one, then you set this in here. And then there are many configuration files that have examples. There's also some documentation and so on. I just want to point this out because I got the question. So, and in general, then there are 2 more things. So the problem, well, I don't know whether it's really a strictly speaking problem, but there are many parameters. They all have, or most have, default values, so we don't see all. There are many more. There are entire sections that don't appear now for 7.2 frontal and so on. So then if this is not given, then the default is used. And on top of that, you can also override the configuration. So I had this before, and maybe I can do this quickly, and I will come to your question in a moment. So before I was running my GNOB normally, and also I take this out. So here's some channel model that I will show. By default, what we see is that we have, for example, a number of hard rounds. So here's 4, is what we discussed before, right? Here's the number of transmission, and then 1, 2, 3, and well, 4th, or the number of arrows retransmission. So 4 hard rounds. And what I want to point out is what you can do is you can override specific parameters. So one example would be now to override here the number of, well, the max MCS. Maybe let's rather go with the other parameter, the number of hard rounds. So basically what we would do is we select one parameters in this Mac RLC section. No, that's not what I wanted to do. Then we set downlink hard round max, and then just for 8, and if we now start it and we override like this, then we will see that it will try to do more hard rounds. So now we see here there's maybe more. So there's just one example. I don't want to really dwell on this specific examples, just to show that you can, when you, for example, experiment and you want to change the gain, you don't have to go into the configuration file, modify, then find, oh, it's not so good, go back into the configuration file. You can do this on the command line and just set a gain, set it to 12, oh, doesn't work as good, then you stop, set it to 6, try to connect the phone, and like this you can iterate a bit faster. And that's actually some kind of feature of the configuration module that many people don't know. So that's the configuration. So yes, sorry, Albert, you had a question. So the problem, as I said before, unfortunately, that is, for example, one field where OAI is actually quite weak, in my opinion. There is no real documentation on all the parameters. And also there are means of, for example, verifying parameters for ranges and so on, but it's not applied consistently. So you can find things out by reading in the code and so on. But unfortunately, the real honest question is no, there's nothing. You can, as I said before, so put complete garbage in there and the GNOB will just run and nothing will work. So unfortunately not, to be honest, just to, also to set the expectations straight. That's actually one thing. I think there's actually one project that will start soon, which also is like meant to make to bring OAI a bit closer to production and so on, what you would expect. So for example, parameter verification, and one of the topics in there is also to bring the configuration module further along, put configuration, put documentation to verify parameters and so on. So I explained that. That's just a little bit about the configuration. As I said, there's a bit more, and if some, I mean, also here, for example, write to the mailing list if there's a question, can I configure that? That's usually probably the fastest way. So I think we won't have the time. I just want to point out that there are these scopes. So we see here screenshots. Basically, there are two types of scopes. There is the so-called X-form scope. This is the historical one, which looks a bit ugly if you want. Sorry, this one. And then there is a newer version, which is the Qt scope. Qt because the GUI framework is called like this. And basically what you can do, we have always two scopes, one for the GNOB side and one for the UI side. And you can, for example, see things such as constellation. So here, for example, you see the IQ constellation diagram for push. So this on the GNOB side, the UI sense, and then you see the little dots. So I mean, maybe you remember that you have the IQ samples, what I was also mentioning before, and you can put them in a constellation show. And here you can have basically a visualization of either IQ, of the LLRs, the channel and pulse response, the actual RX signal, then also throughputs, many things. So there is the Qt scope. I think it also has more features already by now than the original one. To use that is actually quite simple. The easiest is to run build OAI and then build lib enna scope. On the other case, build OAI, build lib enna Qt scope. And then you just need to run the NSoft modem either with the --d Qt option or with only this -d option. And then these will come up. And then, for example, if you generate some traffic, then you will see that the constellation changes and so on. Yes. Yes, you can just use one side. That's possible. Should work. So, I mean, here I would just, I mean, this is something that you can actually also really easily implement using the setup that you already have with RFSim. It works just fine. Then you will likely see relatively clean constellations, such as here. You have like 4 dots and nothing more. The other thing, of course, if you want to see a little bit more action, would be to use channel models. So also in the past, yesterday I said that the RFSim has some kind of channel simulation feature. which is not the full feature because things such as antenna gain and so on are missing, but you can, for example, as a concrete example, just add some noise. And also this is relatively easy with the configuration files that you have already in the workshop material. So basically the only thing you need to do is first these files, they at the end, the configuration files, they reference a channel model description like this, and then you need to add two options. I mean, the first thing is to tell RF simulator that you actually want to have channel modeling, and then you will tell it that you want to have this additive white Gaussian noise channel model, and then you start it, you run. And the first thing that you will see is that it runs a bit slow because there's more computation, of course, that is involved. But then, for example, if we add a specific noise, then we will see that, for example, there are more retransmissions. So let me just demonstrate this quickly. We saw here, this is the configuration file for the Genome B. So I will just show that it's properly done. So here at the end, we have this include channel model rfcmo.conf. Let me also briefly go into that file. So in this file, then there is some description of the channel model and so on. And one of the things then we have here, for example, the model name and the specific type. So this is AWGN, and then I just put a specific noise power of -8. So that's the thing for the Genome B. On the UE, it's kind of the same. So we go into the UE configuration. Here you need to activate this include channel model RFSIMO. Then it references the same file as in the other, as in the Genome B case. And now what I will do, as I said before, I have exactly the same command line, NOSoft modem, RFSIM, SA, the configuration, and then I just enable here channel modeling and I say additive white Gaussian noise. This is for the Genome B, so already we can stop that. Then we have the same on the UE side. Also here, we just add channel model, RF simulator, and additive white Gaussian noise. We add this. So then already you see that now it's running a bit slower and sometimes there's some misdetection and so on, but overall it connects. And the one thing, for example, to see is that now we can do again iPerf as before. So just need to put the proper IP address on which to bind. So now it's 10.004 for the UE, and now I put here the proper IP address. Also, I don't know whether Stefan actually mentioned, but one feature that you can enable in the core network is to statically assign IP addresses, and will remain the same. Okay, and now first of all, it runs a bit slower. So you also see that it now starts to run much slower because apart from all L1, I mean, first the thing is that you need to simulate the channel, and the other thing is that on top also specific things such as LDPC decoding will take longer because it needs to have multiple iterations to actually decode. So not only the channel modeling takes more CPU time, but also the actual L1 will take more time, and that's why everything is running. But on the other hand, we see that it's running properly, and we now see that there are way more retransmission than what we were seeing before. And on top of this, if you now combine this with the scopes that I was showing you before, then you will not see clean constellations, but more like clouds. And then you can, for example, play and increase a little bit the gain, and then you will see bigger clouds. And then, for example, it will not decode properly anymore. And so I just wanted to point this out so that you can try this. I think this should be relatively easy. Yeah. Other questions here? I'm sorry, I need to go quick because it's like 3:30 and I still wanted to show OAM. If there are no more yes, now there are two final things. Well, the one thing that I forgot, you could also dynamically now model the, change the channel model parameters. There's like a small telnet interface, and then using telnet while the Genome B can run, you can log in and modify specific parameters, for example, increase or decrease noise and all these kind of things. So all this is a possibility. There's actually also something to show you how to run multiple UEs, so multiple UEs on the computer in parallel on one Genome B, and then to, for example, see how the system behaves if you then do some traffic and so on. So there's some instructions to do this. I won't go over this because it's basically just running a script and then using the right parameters. So there's furthermore also some information on how to create Docker images yourself. So let's say you developed something and you now want to use this in Docker because after all that's a bit easier maybe, or you want to give this to somebody or deploy this in some kind of lab, then you can also build the Docker images yourself. So there are also instructions on this. And the final thing over which I want to show, just so that you have seen this and so on, is to run with a split. So because in all the examples that we assumed till now is that we had one GNOB. The GNOB talked to the core network. On the other side, there is the UE. And as I also explained, I don't know, yesterday or the day before, there might be reasons, different reasons that you want to split, for example, in a CU and a DU, so the centralized unit and the distributed unit. For example, it would be possible to have one CU that aggregates multiple DUs and that handles handover more efficiently, or so on. So, and I don't want to go as far as simulating handover. First of all, because that's not yet in develop, because I mean, on top, this would be a little bit complicated. I just want to show you how you can then, for example, study in also Wireshark what is happening, okay? So, and for this, I will restart here my capture. I will open a second window, and now instead of having two windows, one for GNOB and one for UE, I will do three windows, where one is for the CU, one is for the DU, and the third is for the UE. So basically, on that, there are actually here also the instructions. So it's simple. You just call NOSoft modem with a specific parameter that doesn't describe entire GNOB, but only the GNOB CU, as you can see here. So that's what I'm doing here. We see NOSoft modem, RFSIM. The RFSIM, by the way, is not necessary. We can take this out to avoid confusion. The RFSIM is only on the DU side because that's kind of the radio interface. And then we have I need to select the proper configuration file. No, and then we have here the configuration for GNOB-CU. And if I now start, we can go to Wireshark and we can already see that the CU talked to the AMF and did this ng setup request, ng setup response. That's what we saw before. Now, on top of this, what I will do now, I mean, you see there's not this periodical output, the radio interface is not initialized and so on. The next thing will be to start this with a DU. So I run again the NOSoft modem here with the RFSIM standalone mode, and then I select the GNOB DU configuration, and I can now start this. So we see that the DU talked to the CU, then we see something about that we accepted the F1 setup request. Now we see that it has been initialized, and now we see here this familiar periodical output about the statistics. If we now go again to Wireshark, what we see on top is that we don't have only the ng setup request and response, but also the F1 setup request and response. And basically the F1 setup request is sent from the DU to the CU, in which the DU informs the CU about various parameters, about, for example, its radio configuration, and also the MIB and SIP1 that it uses. So just to give you an example, so here, for example, now this is the F1 setup request that was sent from the DU that I just started, and basically tells the CU that what is its ID and what is the name and so on. It's all nice. And then in particular, it says what is the cell that it hosts. So there's also one thing that's actually a list, because each DU might have multiple cells and so on. I mean, everything complicated and so on. But what we can, for example, see here is that the DU tells the CU, okay, my PLMN is 00101. So this is what we saw before. We also see things such as the slice that it serves. We see what is the TDD configuration, on which frequency, and all that stuff. So a lot of system information as well. So what is the MIB, what is the SIP1? So then you can also compare what was in the configuration. So you can spend a lot of time just studying that. And now, I mean, my system runs, and the only thing that I need to do is to connect the UE, which is exactly the same UE as before. So I just take out the channel modeling so that it all runs a bit faster. I stop this, and now it will connect, initialize the connection, and then we see that also here gets the PDU session. So with the IP address 10.004 as before, and otherwise the same thing. So maybe the first thing that we can test, just do the iPerf, same thing as before. Okay, do a bit of traffic. The F1 split in itself shouldn't really have that much of an impact on the performance. There's maybe a small impact on the on things such as latency, but depends on the use case. The one thing that I now want to show here on top is, of course, the message exchange that Wireshark then captures is way more complicated. So we could only look here at NG-AP. So this would still be the same what you saw before, but you also see then in between the whole F1 AP communication. So for example, we see that we had this initial UE message that was sent, which went to the AMF, and then something comes back and it needs to forward over F1, and there's a lot of hands and forth. Also this, I mean, as I said, is relatively simple. You just go, you have already the configuration file. The training material points out how you need to start this. And yes, there's some documentation on what is the IP addresses, because then of course you have to configure a couple of things. So the individual configuration files for DU and CU, they are simpler, because those together would make the G0 B configuration, but of course you have some additional IP address configuration and so on. No, so yes, no, you don't need to have, because I mean, there are splits where you need this. So for example, for the frontal, the 7.2, because there you have all this low-level exchange, which really needs to be on time. But one of the reasons why there is this F1 split is because the DU needs to operate at real time, but the CU just treats the messages and there's no real-time requirement. So the way this, I mean, if you also look here at the messages, they are all relatively high level. So in the beginning, you see there's just a lot of like hands and forth where the CU just forwards, the DU forward information between the AMF and the UE. And then, for example, one thing that we see at the end is that at some point, the CU tells, okay, to the DU now create the UE context with the DLB, but there's no real limitation. I mean, if this takes 3 milliseconds longer or 10, no big deal. So for F1, there is not like a synchronization thing. If you go lower on the stack, there's this FAPI and FAPI split between the map and the PHY. There you need to synchronize to down to, well, the interval at which the scheduler operates, so like half a millisecond or something like this. And if you go even further down to the 7.2, well, then you have all this IQ data, and then you really need to use PTP to synchronize the different machines and so on. But in I mean, one of the reasons also why I showed F1 and why me personally, I kind of like this, because it's relatively instructive. You can see what's happening, as I showed you before, the radio information, but on top of that, it remains simple. So, I mean, because you already asked this, and because I pointed out RFSIM is not real time or doesn't operate at real time. So, for example, you cannot use 7.2 split and RFSIM, because then you would need to operate at real time and synchronize the whole thing, and it doesn't work. Complicated. So then on top of that, so this is now another just a screenshot of the whole thing. Then the next thing would be not only split into CU and DU, there's also the E1 split between the CU control plane and the CU user plane. And then you have basically 3 units as shown here, but you still use the same UE configuration, and then it gets even more complicated. Well, let me just stop this. I did this before. So then I run the CUCP as before. Then I run the CUUP. Then I run the DU. I run the UE. And then we see here in Wireshark already in the beginning. No, I need to go here. We see the F1 setup request and response that we had. No, wait, I need to orient myself. Let me just restart this so that we see something that makes sense. Okay, now I know. So also here, what I did now is I have this capture filter set to SCTP so that I get all the SCTP communication, and with that I then capture NGAP, F1AP, and E1AP. And basically what we then here also see that in the beginning we have first the NG setup, request and response. Then we have the E1 CUP E1 setup request and response. Then we have the F1 setup request and response, where all the different parts make a communication. And then you have here most of the time F1AP and NGAP intermixed, but towards the end you also see that there is E1 communication. So for example, we discussed the PDU session resource setup request where the AMF tells the CUCP in that case to create a PDU session. Then before actually creating this on the DU, the CUCP needs to ask the CUP here or request the setup of a bearer. So this is what happens here. Then the F1 has this UI context setup request to update something in the DU. And on top, after all of this is done, then we send down the configuration to the UI. And the whole reasoning here, I mean, as I said before, you can do things such as mobility a little bit more easy when you have one CU, multiple DUs. One reason to have different CUUPs, for example, might be slicing. So one possibility, thing that's being discussed or well implemented, is that you have hardware implementation of a CUUP, which then is very fast, and which you might use for URLC. So maybe one hardware implementation that handles this, and another CUUP that handles for another service, which then maybe goes to the different sliced corner networks. So then only the creativity is the limit of what complicated system you can build. So, and this concludes the part on the runs. Questions? I know it's fast, but you have the material. We have maybe a final 20 minutes. Let's go to OAM.